Yesterday I was
All right. Let's start with the afternoon session. So our first talk will be Andrei Bernevig, who will tell us about twisted bilayer graphene and
Well, it's actually the narrative on the production and talked about this. I'm just going to partition myself into two parts. The first part is the very quick some use that we will have. Most of it are published and designed by
Take the microphone.
microphone. Oh,
Yeah.
I really need it.
No, it's needed.
It's needed. Okay.
The rest is.
Okay, and the second part is going to be about endpoint twisting, and I hope I get to it. We'll go very fast through this part. Most of the work here has been done by Keshav and Yulin, and there's a lot of past work that I'm going to refer to done by these people. These are just the people that have been junior. They've been working on this for many years. So I'm delighted to have collaborated with all of them who have really done the work. So as Eris has already shown, we're just going to start with twisted bilayer in this basis, which makes the interactions very clear. The interactions are between the localized F electrons. And if you take the Bicester-McDonald model at its, or the DFT at its truth, then you're going to find the following parameters for the hybridization between the F and the C electrons, and for the bandwidth of the Bicester. This M here is the bandwidth of the Bicester-McDonald. It's really 2 times M is the gamma point separation between the Bicester-McDonald bands. So these are the parameters. Quickly now, since the electrons are here, a picture of what we're going to do is that you take the Coulomb interaction, you project it into this F basis, F and C basis, and you find many interactions. A lot of them, all of them are local, at least with the F electrons. The most important one that we're looking at, just like Eretz and Patrick, is the Hubbard U for the F electrons. There's other ones like spin between the F and the C electrons, some SU4 spin, that also will create scattering, as I'll show you later, and that might need to be analyzed. But the moral of the story is that these F electrons, which set a charge neutrality, don't like to sit at charge neutrality. They can gain energy by splitting, either in a multi-insulator way. But this C electron here, which in the limit of Bicester-McDonald's bandwidth being 0, has no gap here. So there's 2 of them, and there's 2 Diracs. But in the limit of finite Bicester-McDonald bandwidth, it becomes a double vortex here. This double vortex is protected by topology and cannot open a gap. So here you get to this so-called most semi-metal thing that we're going to analyze a little bit. As I go away from charge neutrality, I start filling up these electrons, and this we're going to call the local moment regions, where basically I have some local moments that have 4 Hubbard bands, and then I fill up the C electrons, and then in between them, I'm going to have fluctuations between F and C when I basically, my Fermi level lead somewhere here. I don't have time to go into it. But if you do the DMFT, and this is what I wanted to compare it with Stefan Natzberger's recent experiment, what you get is that not an integer filling, and not, well, in some cases integer filling too, but not at, but in most cases away from integer filling. What you get is a series of transitions. First, high temperature, you get Hubbard bands. There's another Hubbard band somewhere else to diffuse to C. Hubbard bands, for example, this one. And this is the STM of Stefan. Some of it, this is all done on tri-layer, for example, DMFT, and iterative perturbation theory. But basically, at a lower temperature, you get a condo peak or a zero bias resonance that becomes coherent and that pulls weight from the Hubbard bands. And this is the theory, and this is the experiment. And how do we interpret this? Well, there's two things. I'm not saying this is proof, but there's certainly two things that one should look at. Thing number one is that as you lower the temperature in the experiment, you start seeing a zero bias peak that develops in the STM data, just like here. Thing number two, the zero bias peak, if you normalize it by the lowest temperature one that you get, if you go even lower, it splits. If you normalize it by the lower temperature one that you get, and then put thermal broadening, disappears much faster than the thermal broadening. Thermal broadening is the dashed curve, so you can see how it disappears. This is exactly the same as here. If I had put thermal broadening here, it would still be very high here. So this matches this DMFT calculation. Then the other thing is that it disappears in a clear way on one side of the bias voltage. Okay, so it's pulling weight from one band and disappear from one of the Hubbard bands and disappears, or mostly, and disappears in that direction. And you can see the trend the same in the calculation. And all these things we can sort of understand through a DMFT calculation. But then if you go to even lower temperature, and this is the hierarchy of states that is claimed, at least in this experiment and in the calculations that are attached with it, to happen. If you go to even lower temperature, out of this condo peak develops the famous, well, at integer fillings, this is a partial IKS state because it's not at integer fillings, but develops this famous IKS state that was predicted from Hodge-Fox studies by Eve, Nick, and Sid and co-authors. So basically what happens is that the condo peak splits then, you can see the splitting here, and becomes two peaks. This is still a metal because you're not an integer filling, and there's even a further transition at even a lower temperature, where out of this metal, you develop another gap, and that's the superconducting gap. So it's a hierarchy of gaps that was seen in STM, and it wasn't really clear in transport studies, but a slide from our friend Dmitry Efetov's group, where they analyzed 18 different samples that they take, they see this previously unoverlooked metallic dome here. So you can see that there's a metallic dome, almost always the superconductivity appears here, and some other samples, but not in all 18. Almost all, I think 17 out of 18 have a superconducting dome here. There's some other superconducting domes here, but there's a previously overlooked region of temperature where you get a metallic dome out of which the superconductor appears, and we interpret then that as the coherent condo peak plus the, or of course, IKS state that develops. It's all a metal in that case.
Andrei,
yeah.
What is a metallic dome at finite temperature?
This one.
Yeah, no, but what does it mean?
Well, the way you're asking me to define it for the way Efetov defines it. So they define it as some power of the resistivity. And semi-metal would be a peak, then power 2 would be a metal, and etc.
So it's the power of rho versus T,
basically. So
IVC ordered metal.
Sorry.
This IVC ordered metal.
Well, it depends. I think the ordering. I think there's actually a 3-step. What we think is there's a 3-step process. At least the STM does see a 3-step process. What we think is the first step is you develop the condo, you develop a zero bias peak. The zero bias peak becomes a Fermi liquid, then it orders into a condo, into a IKS state, and this IKS state is still metallic because you're a fractional filling that splits the peak, but then it's still a metal, so then there's a further gap. This is related to Pablo's 2-gap paper, and the numbers match. They don't exactly match, but they match much better than before. There's a further gap, the first splitting of which is the superconducting gap. So I think the superconducting gap is appearing under an IKS state that appears under the condo peak. That's the okay. So now I wanted to very quickly get to. I'm just going to pass very quickly to this because Eric and Patrick already spoke about it. This is obviously there's Hubbard bands. Let's forget about the condo for now. Let's go into the region of Hubbard bands, for example, at half filling. This vortex here, you can't split it if you maintain the symmetry. So if it's a symmetric thing, you can't split it. And you get this type of spectral function as was shown by Eretz and Patrick. This is a fake broadening. It doesn't exist in the Hubbard-1 approximation, but it will exist in the approximations that I'll show later. And, you know, you can say, well, you can declare victory and say that, of course, it matches, for example, the DMFT, but of course it matches Eretz's Monte Carlo, etc. Even the scales match without, this is without fitting, okay? You just take the parameters of the Vista-McDonald model, you plug them into the UNT, the scales would match if I would show you Charles' paper. But as usual, and this is, you know, credit to Oscar and his group that basically got us thinking also about this. So, basically, there's other possibilities. So you can see that Chahal's experiment sees basically a big blob here, which suggests a finite scattering rate, or at least some larger region of spectral weight of these C electrons. The DMFT at nu equals 0 without strain, or with strain, as Jonah put strain, Jonah and Oscar put strain in this model. You see, basically without strain, it's basically the same. It's just that with strain, there's a without strain, there's a lot more fluctuations. This is the symmetric state. This is the not spontaneously, but strain broken Hartree-Fock state, basically strain same metal. There's a lot more fluctuations. There's a lot more diffusive bands here than here. But basically, the moral of the story is they look kind of the same, with the exception that this one actually looks a little bit fatter onto the C electrons here. If I just had some matrix elements, that could be, you know, that could give you some broadening. It's sharp, but the extent in space is a bit fatter. So, you know, there's the question of how exactly which of these scenarios to look at. And what I want to point out is there's a way of differentiating between them. But before that, I'm just going to go and point out this exactly what Eretz. This is basically the third time you see a slide like this. There's a small parameter either way, whether you're in the projected limit or whether you're not in the projected limit. There's a small parameter in this model, and this is because you can't get to this, you know, density of states that's to this small region in momentum space where you have Barry curvature without a linear dispersion. The linear dispersion will basically make, and large velocity will make that rock go away fast, and you're going to get this small parameter. But because you have linear dispersion, you're going to have density of states that's linear. What Eretz said, density of states at omega equals u over u is constant, so u disappears, and you basically have this as a small parameter. This parameter is s squared of Patrick's, or the parameter is equal to s squared. This is the Hubbard-1 approximation of the topological heavy fermion model with finite bandwidth of the Bicester-McDonald. The Bicester-McDonald bandwidth, you can see, is finite because there's not a 2 Dirac, there's double vortex here. So there's in the Hubbard-1 approximation, bands are located plus or minus u over 2. We know that from DMFT, the bands are actually, with the same parameter, are actually below 20. So there's a large normalization. So how do you get that? I don't want, I'm running out of time, so I'm not going to go through a dictionary between the non-local moments and the Hubbard-1 approximation of the heavy fermions and then further approximations. But basically, the moral of the story is that if you do a hybridization expansion, what you're going to get for these spectral functions are the following properties. And this is the same as Vittori and Berg and Leonid's and Felix, and yesterday there was a paper by Patrick, similar. Basically, if you don't take n exactly, they're exactly the same results. What you obtain is the following. The Hubbard bands, now they are not sharp anymore. They have a lifetime that, you know, has this expression. These fermions at the gamma point, there's two kinds of fermions at the gamma point. There's the one that remains gapless, and there's the one that splits by the Bicester-McDonald bandwidth, okay? The one that remains gapless, okay, has, if m is equal to 0, if there's no bandwidth, it has a lifetime that's proportional to K, okay? So it's very sharp. And when you put bandwidth, since it becomes quadratic, when you put bandwidth in the Bister-McDonald model, i.e. this difference is the bandwidth of the Bister-McDonald model, this is still gapless, but it's now quadratic, and it gets a finite relaxation time, okay? Now, there's another scattering mechanism which has to do with the SU4 spin, but I won't discuss that. Now, the Hubble bands renormalize, and you can see they renormalize down from U1/2. So this is no longer U1/2, they normalize down. But I wanted to point out that the actual expansion parameter is not the hybridization. Expansion is hybridization fraction times NF plus 1. And I think we agree with, right, Eretz, in your paper, you also have to tune down this matrix element. If this matrix element, this S squared, this kappa, this size in the Brion zone, where the C fermions hybridize the strongest with the F fermions. If we didn't tune it down by a factor of 4, this would be broadened like no other. You wouldn't be able to see the Hubble bands. So I would say we still, you wouldn't match the DMFT or the Monte Carlo, right? If you took the actual value of K, of kappa, you have to tune it down. So this basically, I think, tells you that this parameter, when you multiply by the number of fermions plus 1, has issues in the expansion. Okay. Again, these 4 papers did basically similar things. This guy here with finite Bister-McDonald bandwidth of the bands, which is equal to this splitting, which is equal to M. This guy here gets a lifetime, tiny, but a lifetime. And this guy, these bands are still sharp because of the difference in representations without strain. But because the lifetimes are very sharp, now it poses questions of what is that big blob in the Weizmann experiment. And that's even forgetting about non-integer filling, just an integer filling. So what's this big blob in the Weizmann experiment, and what are the other possibilities? And I'm not sure if it's really other possibilities or if it's what happens, because it's, I would say, matches a little bit. Well, let me not say this yet, but let me give you another possibility that certainly matches spectral Landau level data. So there's 2 types of possibilities. If there's strain in the system, you can have a strain semimetal. That's a Hartree-Fock state, basically. If you don't have strain, you have a this gapless semimetal. And what you can do is, for the strain semimetal, you can basically take the mean field Hamiltonian, so you're going to have some, Hartree-Fock corrections that are quite sizable, but it's effectively the F electrons get split by strain, and that splitting gets enhanced by the interactions. When you do this, you are going to get continuum Landau levels from the C electrons, plus hybridization, plus some F electrons that are projected into the magnetic translation group. This is a paper that by Keshav, Jonah, and Oscar, and other people. In 2023, I think I'm missing the year, 2024. Okay, so this strain semimetal, we know how to do Landau levels. So it's Mott semimetal is a little bit stranger because it's a Mott state and we're going to do Landau levels in a Mott state. But I think we figured out for the first time how to do this. So what happens is that you take the self energy of the F electrons, okay, and you want to put Landau levels in a self energy of the F electrons in a Mott state. What you do then is you write your Hamiltonian in auxiliary, you introduce auxiliary fields, such that if you integrate out the auxiliary fields, you're going to get the same self energy that you had before the auxiliary fields. This is an auxiliary field method that's well known, really. But now you have, once you introduced the auxiliary fields, you have a quadratic Hamiltonian, and in the heavy fermion theory, you can just put in the Landau quantization, or the Landau, the minimal substitution onto the C electrons, which are the ones that are really mobile. So if you do this,
The A there is a fermion boson.
it's what?
The small a. The A.
A is auxiliary.
And
These are auxiliary fermions that you introduce. So the purpose,
so they are fermions.
the fermions, when you integrate this out, I'm going to obtain the same self energy as the interacting Mott problem.
And the epsilon alpha gapped or gapless.
The epsilon alpha are the poles of this energy, of this self energy. You can see it. So there's a one-to-one mapping. See, you give me a self energy, I map it into quadratic Hamiltonian. I integrate that, I'm going to get this. Now I'm here, so I'm going to put minimal substitutions on the C electron, okay, which are part of the whatever gammas, blah blah. And gonna do minimal substitution.
So it's the same as diagonalizing this effective quadratic Hamiltonian and then obtain new excitations and expressing.
Yeah, well, the problem is you have a Mott state, right? So you have a Mott state that's defined as some self-energy. How do you put in Landau levels on it, right? In the semi-fermion description, it's very easy to put Landau levels. You put in the auxiliary basis. In auxiliary basis, you have the C electrons. Those go by minimal substitution because they're free, basically. There's another trick. The fact that the F electrons are far away is important, the plus minus U, effectively. Yes.
And
I want to move, but yes.
I'm just confused how you can only do minimal substitution for one, given that you tunnel between them.
Oh, you have to
the
read,
auxiliary
don't
ones
worry
have a
about it. You have
charge.
to read this paper. Then this paper was all figured out how to do it. It's very complicated. It will take me basically, well, I wouldn't be able to reproduce it right now, but it would take me certainly a month to explain it as it took us. But you have the correct counting in the end. It all works out. Okay, so brief, the situation becomes the following. Now, here, let me make the Bister-McDonald. This is the easy limit. Make the Bister-McDonald bandwidth 0. If I make the Bister-McDonald bandwidth 0, there's going to be 2 Dirac fermions here. Okay, 2 Dirac fermions here. These 2 Dirac fermions will give you the phase diagram, C minus 4 C4 per valley per spin. So times 8. And then it will skip to C equals to 12. There will be no C equals 8. Okay. In the realistic problem, there will be C equals 8, but it's basically very clear that there's a huge gap at 4, very little 0 gap in this idealized limit, and small gap at 12. There's some residues here that are not 1 because of the auxiliary fermions. Strain semi-metal, what happens with the strain semi-metal is strain has now split one of these Diracs, moved them up and down, and you have a single degenerate quadratic touching here. This is in the limit, in a very artificial limit of the strain, where the strain goes only through the F electrons, but it's a good limit to understand the problem. I have just a quadratic mode here. This quadratic mode here gives 2 levels per valley per spin, minus 4 to 4, but now I get an 8 fundamentally, and the gap between 8 and 12 is larger from 8 to 12. So Keshav did not only self-consistent, but a huge amount of work. And this is the actual thing that happens away from this easy limit. What happens, you have relaxation, you have strain. This relaxation immediately shows up that the spectrum is not particle hole symmetric. But the moral of the story is that the gap, the C equals 4 gap is the largest. The C equals 12 gap is also large, and the C equals 8 gap is sensitive to the magnetic flux. So you can see how it moves around to the magnetic flux. So for the semi-metal, whereas for the Mott semi-metal, whereas in the strain case, there's always, no matter what you do, a hierarchy where the C equals 4 gap is larger than C equals 8 is larger than C equals 12, and this just has to do with the way you split these double vortex and Dirac fermions. Now, what the experiment shows, and this is, I think, Ben Feldman's experiment, what the experiment shows is the following: T equals 4 gap, largest, T equals 8, next one, T equals 12, next one. So it's more consistent with a strained semi-metal, we would say. Okay, so that's I guess I'm just going to move. Any questions on the twisted bilayer part? Yes.
Yeah. So when you apply the field, you order some moments, particularly because there's an orbital between valleys. There's some large orbital, and that changes the self energies.
I mean, okay. So you can do things self-consistently if you want. Okay. Well, here we didn't order any moments. Okay, we just took the Mott semi-metal. Okay, and then do it in auxiliary field, and then put in. Of course, actually. Right, Keshav did self-consistent calculations where I think these are actually taken into account. Probably the magnet, the change of the right. You basically you're saying you're just going to have some magnetic moments that we're going to couple.
Yeah.
Yeah. I'm not sure if those are first order effects.
They are.
I would say, well, then do a calculation and show how the first order effect. I claim that they might not be, because I claim these are first order effects. And if you're going to obtain with a Mott semi-metal a gap of 12 that's smaller than the gap at 8, then we can chat about it. Okay. So any other questions? So now I wanted to basically go to the main part of my talk, which is the endpoint twisting platform. And this was done by mostly Dumitru, E, and Hangshi, but now, and there's, I want to present some work that Sid has been doing on it with Dumitru. More of the story, most of the things that we looked so far, K-point twisting, but there's a particular nice endpoint twisting series of materials that I can tell you about. And these materials are basically of this class. They exist in these crystals. They look pretty shiny and pretty nice, and they've been exfoliated and twisted. Now, this endpoint materials have, actually, they're kind of neat because they have a conduction band minimum at the endpoint and a valence band maximum at the gamma point. So depending on whether you put the gate at, you gate into the conduction band or the valence band, you can have endpoint and gamma point twisting. Okay, and the band structure looks pretty simple, so you can actually have some theoretical intuition. Now, the theoretical intuition comes from basically doing some DFT first, and there's several types of stacking. There's A stacking, where you take 2 of these layers and twist them, take 2 of these layers, rotate them by 180 and twist them. They produce similar looking band structures, but they're actually very different. So this takes, about 6 months to do if you do it with, because, if you check out all the pseudo potentials. But this is the variation of A twisting and AB twisting from 30 degrees to 3.8 degrees, 3.89 degrees with lattice relaxation. And you can see the appearance of flat bands. They're actually quite flat. You can see that there's not regions of K-space where this band is closer to this, but likely this band is topologically trivial, and it is, and likely this band is topologically trivial, and it is. Now, you can see the twisted version of the samples at 5 degrees waiting to go into STM in the Galogeras group at the APC. This is 5-degree twisting. So let's analyze what happens in these SNSE. And there's 2 papers about this from our group and from Alan's group. Basically, the moral of the story is that there's several sets of flat bands. Okay, but we're going to focus on the first set of flat bands. And this is the first set of flat bands in AA, which are probably going to be the only one that I have time to talk about. And this is the first set of flat bands in the AB stacked. In the AA stacked, this is the second set, so forget about it. If you look at the vanirization, and we understand why, the vanirization gives you an orbital at the hexagonal, a little bit away from the hexagonal point. Now, how many bands are there? Well, the endpoint, there's 3 endpoints, right? The original system was triangular. There's 3 endpoints, the time reverse invariant points. There's 2 spins, so there's actually 6 bands here. Okay, so each of these orbitals, each of these Vani orbitals here that we're going to focus on, they come with a valley flavor: valley M1, valley M2, valley M3, and with the spin flavor. The spin orbit coupling is very tiny here. Spin flavor up and down. So let's focus on these guys. And it turns out, other people have written a little bit of papers about endpoint twisting, but they missed a fundamental thing, that there's a non-symmetric symmetry in momentum space in the system that gives you a one-dimensionality of the system. Normally, when I write down symmetries, the symmetries that I write down basically don't translate my momentum. They just change my momentum based on the symmetry of this generator. So look what happens at the endpoint. This is one valley at the endpoint. This is the K-point lattice, the plane wave lattice of the endpoint. This is the endpoint of the upper one, endpoint of the lower one. Okay, and if I look at the first order, just the nearest neighbor couplings between the Moiré potential, you can see that if I change, there's the same distance from here to here, if I change this dot to this dot and translate it, okay, so if I change this dot to this dot and translate, I'm going to get the same Hamiltonian. That translation is translation by half a lattice vector, and this change of the blue to the orange is a mirror symmetry onto the z-plane. So I change the upper plane to the lower plane. So there's a mirror, non-symmetric mirror symmetry that changes your momentum, makes your momentum go to k from K to K plus pi and shifts the layers. This mirror symmetry, which is not crystallographic, you cannot get in. It's actually there in the zero, in the rigid twisting approximation, is clearly seen in ab initio. For example, you can see that the Fermi surface here has a one-dimensional, in this band has a one-dimensional structure, and in a simplified model, it's really actually one-dimensional. What does it give you? Well, it gives you one-dimensionality. This mirror symmetry in momentum space gives you one-dimensionality. Why? Well, if I'm going to look at this mirror symmetry, then and find these commutations with the translation operators, the translation operator in the y direction commutes with it, okay? But the one where you change by pi in the m1 direction anti-commutes with the mirror symmetry. And this is the translation momentum space by pi. So then it means that these chains and these chains, I can label them by different mirror eigenvalues. So the chains separated by a translation in the m1 direction have different mirror eigenvalues. So it means that to first order, there's no hopping between these two chains. Now there's going to be hopping between this one and the next one here, but this next nearest order coupling, and you've seen how localized these orbitals are. So it's an order basically of 20 to 30 smaller. So to first order, we only have per valley hopping in this direction, hopping in this direction, hopping in this direction, and no hopping in between chains. So the model that we have is 3 orbitals, color means valley, and this is for the upper layer. For the lower layer, the binarization, very tiny, very localized, and the hoppings between them are valley selective. So the red orbitals hopping only in this direction, the blue one in this, the orange one in this. Okay? Now, unfortunately, or fortunately for us to make it interesting, these orbitals from different values are all close together. So the Hubbard interaction will combine all of them. So you got a dimensionality reduction where the hopping is one-dimensional, but the Hubbard is two-dimensional. Okay, so we'll combine all of them. So what happens here is that the dominant on-site repulsion is the Hubbard one, and the Mott insulator state, you will have, sorry, 1 second, you will have a TJ model that is one-dimensional. This TJ model is one-dimensional for the red valley in this dimension, for the blue valley in this dimension, for the orange valley in this direction. The reason is that the TJ Hamiltonian follows the hopping, which is one-dimensional. So we just need to understand in the strong coupling limit what is the phase diagram of this Hamiltonian. And it turns out that it depends on the filling. At filling 1, you're basically looking at these spin chains, but because of this charge term that appears, the system prefers to make short spin chains, i.e. dimers. It doesn't like to make long spin chains. This is some DMRG and Bethe-Ansatz calculation that you can prove very easily that it likes short dimers. So at filling 1, where you have many types of freedom, this type of configuration is the ground state. There's many of them. There's a large entropy of them. But basically, the moral of the story is that the red valley forms a dimer with this one, a spin singlet, but doesn't want to form another spin singlet with
One means one-fold, three.
1/4. No. This means one. So it's filling 1/6 of the. So the first band, there's 3 valleys times 2 spins. So there's 6 in this flat band. This means 1 electron. So this is half filling. This is filling 3. So filling 1, what happens is I'm just filling each site with a valley. Okay. So this I'm filling with valley red. I'm forming a dimer with valley red here. Because it wants to form short spin chains, I cannot form another dimer with valley red here. So I have to switch the valley. If I switch the valley, this forms, and there's this extensive degeneracy of these guys. At filling 2, however, you don't no longer have an extensive degeneracy of a finite degeneracy and valence bond solid state of these configurations. And at filling 3, we need to have 3 electrons per valley, okay, not per valley, per site. So half filled, then the only possibility is spin chain in this direction, spin chain in this direction, uncoupled spin chains in this direction. So 3 uncoupled spin chains. Now, in the last 2 minutes, I want to advertise.
This previous plot, what is the tunneling? So you just, when you have these kind of dimers, you
Yeah.
say classical, are there any tunneling in between?
So that's a second order effect. In this case, there's no tunneling. So so the tunneling would come from, for example, the next nearest neighbor hopping. So these chains are divided by mirror eigenvalues. They cannot hop, but of course this can hop here. So it's an order basically 1/20th of the first tunneling. So I would expect it's a 1/20th effect. We don't know the ground state there. So we just did the very simple thing. But of course there will be tunneling, and we'll select among this huge degeneracy of ground configuration. Okay. But all of that within the U goes to infinity limit. Right? Yes. Stopping in 10 seconds. U infinity limit, but actually it turns out that this problem is Monte Carlo sign free, even away from U goes to infinity limit. So Dumitru and Sid basically recognized that because of its one-dimensionality in each valley, you can basically make you can choose a gauge where all the elements of the Hamiltonian are positive, for example, and you can do stochastic series expansion. And this entire phase diagram at here is sign-free stochastic series expansion sign-free. So these are the new unpublished data that basically show you as you, I guess, lower the temperature, the formation of some insulating states. Here, notice, because of the high dimensionality, the Mott transition is actually U equals to 60, not at U equals to 4, right? Usually U equals to 3 or something, but here, because of the high, it's U equals to 6. So here they don't get Mott insulated, but you can see kind of like peaks in compressibility. And then this is what happens when you increase U. And then you're going to see basically here Mott-Wigner states that are developing. This is actually data. This is their calculation on stochastic expansion Monte Carlo. Okay, so that's my talk. There's another, the AB stack is also very interesting, but I don't have time to go through it. It can basically be mapped into a charge glass problem, but I want to end here and to basically say that these have been twisted, so data should come out soon. Thank you very much for your attention.
Question. So I think both you and Aries mentioned that this string has like a amplification effect because of interactions.
There's just a Hartree-Fock.
Right. So is it connected to some proximity to a nematic instability or no? Is it not really?
Well, I mean, so the nematic instability of the heavy
Yes. Without yes, yeah.
Yeah, I've never computed this, but I would. Yeah, actually, I don't know.
Okay, there's a large pneumatic susceptibility.
Huh?
There's a large pneumatic susceptibility.
Yeah, but I don't know what to do with like how close it is.
Yeah.
That's a Curie law. So it's a big susceptibility at low temperature.
But do you couple it? Do you know if in your calculation you're coupling the strain to that? Or?
Yeah, you do.
Oh, you do.
Well, the strain just splits the heavy electron, so it's a first order.
Yeah.
Okay.
The only thing, but I don't know. Yeah, I don't know where it stands among all this. There's a lot of there's a huge amount of instabilities here. I don't know where it sits, but it's a first order effect. The only thing you expect, because if you look at what strain does, you can just visualize it by drawing a Mathematica file. All the Moiré moves like crazy, right? If you just and it has to have a huge effect on DF electrons.
Okay.
Those are just and it does. That's what I found out.
Yeah, it behaves like all the other flavors. So it's almost like a Zeeman field.
Okay. I see. Andrei.
Yeah. Very nice question. this wonderful story about 3 chains. Have anything like this been seen in an experiment? Has any one-dimensional physics been discovered?
Well, the experiments are still ongoing,
Mhm.
but what I can tell you that has been seen in experiments is insulating states. So Mott insulators do exist. So far, has nothing been seen that would say that this is wrong, but all of that stuff is still is not out.
Any
Yeah, for this classical spin liquid, when you imagine cooling it down and getting the ground state, are there any constraints on what kinds of ground states you could get? Because
You mean by Lieb-Matthias-Schulz constraints?
but you're in a weirder Hilbert space, so I'm wondering
That's
if there are
right,
tighter
so-
constraints. If you assume you're within this dimer covering.
Well, if you're in this dimer covering, there's a huge amount of there's an exponential degeneracy.
Yeah.
So, I don't want to say stuff that I don't know. So the real answer is we haven't looked into it. And by the way, this stochastic series expansion won't help you there, because if you want to break the degeneracy, you need next nearest neighbor, in which case it's not Monte Carlo sign free anymore. The only thing that stochastic, well, not the only thing, but the thing that stochastic series expansion gives you is it gives you the phase diagram without taking t to 0 or u to infinity. It gives you the phase diagram for any t and u, but t along the chain. It won't give you t between chains, because that will break the Monte Carlo sign free.
Is there like a simple dimer model you can write down within this like low energy space that's with the T perp?
Well, so in this low energy space, so here's the thing. So in this low energy space, these are not your usual dimers on the square lattice. The usual dimers on the square lattice are non-orthogonal, right? Because you've got, but here they're because they're valley colored, they're all orthogonal. So it's basically right. There's it's an orthogonal basis. Each of these configurations is orthonormal to any of the other ones, because you don't have this issue that you have in the square lattice or in any, or just spin 1/2 dimers.
Right. Well, let's move on. So thank Andrei. And next up is Longju.
Okay, first of all, I'd like to thank the organizer for this annual festival in Minnesota, in Minneapolis. I'm going to talk about superconductivities, and there are really many different superconductivities I'm going to talk about, and as I will show, most of them are unconventional. So they are unconventional different ways, and one of them I want to highlight is the Chiral superconductor. But as I promised, there will be many. So Rhombohedral graphene, I don't need much introduction to it, because Alan and Matt has already introduced the basics. But just to show you, you actually can directly visualize different stacking domains in exfoliated flakes. And the trick is to use infrared light instead of visible light, because that's more sensitive to low energy band structure difference, corresponding to different stacking orders. And you look at the image, you see different patches that you wouldn't see in the visible image. Of course, the absolute contrast to here cannot tell you what stacking order they have, but Raman spectroscopy can differentiate these different stacking orders very reliably. This is a targeting at a specific phonon mode, And as you can see, there's a small difference between Rhombohedral and the Bernal stacking, but that's very reliable. So you can use this to double check the contrast you got here and identify where's Rhombohedral or where's Bernal stacking. Rhombohedral is very interesting in two senses. Number one, it has a flat electronic band structure. Without gating, it has this energy proportional to momentum to the nth order dispersion relation and is a layer number. Of course, this is an oversimplified model by neglecting some of the small hoppings, but it's roughly right if the layer number is not too big. So you got zero band gap to begin with, you get a pair of bands that's touching at zero energy, and that's already very, very flat in terms of the band dispersion and give you a huge peak of density states in the pristine form without gate, right? So you don't need Moray to get flat band. And in this particular system, you get something that's even better than just the Bilayer graphene because you get another dimension, another knob to tune the band structure, which is the gate electric field. So that can open up the band gap. And for the conduction band case, it can squeeze the bottom of the conduction band and make the density states even bigger than the density states that we got from the sum of the two degenerate bands without gate. So you get the electrical tunability, you can massage this band flatness very precisely by controlling the gate electric field, and you can study what this big density states is going to give you. The other reason that you want to look at the Rhombohedral stacking order is because this is also the place to look for big Berry curvature, quantum geometry, and the possibly topological effect. So K and K prime form a pair of time versus symmetry relative pairs in momentum space. And when you open up the band gap, you get Berry curvature distributed in the K and K prime value in a fashion that the same state has opposite Berry curvature. So when they are equally populated, the curves cancel each other to preserve time versus symmetry. And once you have big Berry curvature, you can start to think about how to detect them in experiment. For example, you can integrate the Berry curvature to detect the Hall signal at the zero magnetic field, the anomalous Hall effect, or you can detect the associated effect that the wave packet will rotate around the center of itself and give you orbital magnetism. Of course, now these are detectable if you have equal population in the two values. If they are symmetric, the time versus symmetry will not be big, right? They will cancel. You have zero anomalous Hall resistance, and you have zero orbital magnetization. And this is exactly where the flat band help you, because when the density space is big enough, the exchange interaction of spin or value or a combination of them can take place. And in this case, it can break the value symmetry between K and K prime. Then you can harvest the net contribution from one of the value, and you can detect it very easily in experiment. This underscores all kinds of interesting phases that you may get from Rhombohedral graphene, including insulator, metal, superconductor, and possibly Wegener crystal. Okay, so my student Tohan made a nice animation to show how this band flattening and the Berry curvature tunability by gate electric field look like by dialing the interlayer potential UD here. As you can see, you have pretty flat band, and the conductor band is actually getting more and more flat until some optimize the interlayer potential. Then it develops this Mexican hat shape. While the valence band starts to be Mexican hat, even at the zero displacement field. So in that sense, you would expect more interesting things happen on the electron dope side because you have a reasonable range to tune from not flat, but not so flat, and optimal flat, and not so flat. And this can be seen if you calculate the density states. For this is the whole doping side, this is the electron dope side. As you can tell, there's a very bright blob here on the electron dope side, and that corresponds to when the bottom of the conduction band become really, really flat, and that gives you a huge density states that's bigger than in any other condition that you may find in the system. Definitely bigger than the whole doping side. Okay, so we set the stage for interesting phenomena, maybe driven by electron correlation, and maybe accompanied by topology, quantum geometry, orbital magnetism, right? Since today I'm going to focus on superconductivity, let's just talk about superconductivity. This is something that all of you are familiar with. Superconductivity is first seen in twisted graphene. And later, Andrei Jian was the first one to remind us, you don't need Moray to get superconductivity in graphene. This was first shown in the ABC trilayer graphene. This is the SC1, SC2. SC1 was very well developed at that point. It goes to zero resistance. SC2 has a relatively big residue, but the TC is also low. And later, it was shown that you even in the AB bilayer graphene, you can have superconductivity, but it requires an application of the in-plane magnetic field. Later, Stefan and Nappert shows that, oh, if you put bilayer graphene on a TMD layer, then you don't need the in-plane magnetic field. You can stabilize the superconductivity at zero magnetic field. So these are the efforts that people have done in the Rhombohedral, the crystalline graphene series. And next, I'm going to show you our data. Okay, by the way, these are the same references as shown on the previous page. So we first did an experiment where we really want to understand what does the spin-off coupling do to graphene superconductivity. So we chose a 3-layer Rhombohedral graphene ABM stack, and we put TMD on both sides. In this particular device, we put TMD on both sides in a way that they are rotated by 180 degrees. In fact, that was not only to look for superconductivity, that's what actually to engineer a quantum spin Hall state that is supposed to be existing at 0D and 0N. That's why we have to have a 180-degree orientation. We didn't see quantum spin Hall effect there, but we see a dramatic change of the superconductivity landscape in trilayer graphene compared to what Andrei first reported. Just to flash show this first. SC1 is at the boundary between a half metal and some other states, while SC2 is here. When you have strong enough spectral coupling introduced to the Rhombohedral trilayer graphene, you don't see SC1 at all. It's completely cured. I believe this is the first example that SOC does not universally enhance superconductivity. Because before this experiment on crystalline or twisted bilayer graphene all suggest that SOC help superconductivity. This is exactly the opposite. But at the same time, spin-off coupling seems to induce some new superconducting state. One of them is located here, and the other one is on the electron side. I think this is somewhat similar to what one of the superconducting state Andrei's student have in his thesis, never published, but with SOC, this got enhanced dramatically. Well, the one that I'm going to focus on today is actually located at a different location. But before that, I'll show you that in these different regions, you have different symmetry breaking ground state. Here's half metal, here's quarter metal. And quarter metal has two parts. One is a speed value polarized quarter metal, while close to the tip, I think this is a IBC. And here is also half metal. So I want to focus on this little corner here that you don't really see anything, but if I zoom in there and make my pixels smaller, you actually can see a superconducting state that's wrapping around this quarter metal. Okay, and we call this as SC5. This is a new superconducting state, has a TC around 70 millikelvin. It was not there without. Yes.
So in both of these, or all three of these superconductors, the resistance actually goes to zero. Is that right?
I think so.
So just previously, you get in terms of this phase diagram, superconductivity without TMD was where?
Superconductivity without TMD, SC1 is supposed to be here.
So it's somewhere the ones that you see in the presence of TMD is somewhere at the boundary of previous superconductivity.
SC1 is here. So okay, on this map, I can put this new superconductivity state I will observe to be here.
Okay.
And for some reason, in any of our device, in all of our devices, we never see SC2. I have no idea. We never see SC2. Right? Let's focus on SC5. SC5 wrap around this corner. And if you try to do fermiology, where you apply magnetic field, do quantum oscillation, do Fourier transform, you find that this corner is actually at the boundary between several different parent states. It's really complicated. So I cannot really tell you what is the parent state of this state of this superconductivity, but our feeling is that because the right hand side is half metal, and this corner here is a full metal with sort of imbalance in the isospin flavor. What they have in common is a half metal like this. So we tend to think this is the parent state of this SC5, and it has balanced the valley. It also has balanced the spin, which is not surprising because there's strong spin of the coupling coming from TMD. So you get the opposite spin and the opposite valley, and there's a spin valley block. Experimentally, what is interesting about this SC5 is that, first you can apply in-plane magnetic field and ask, what does the superconductivity do, right? Usually, in-plane magnetic field kills superconductivity, under the so-called Pauli limit, if it's S-wave. Well, because the TC here is really low, we know what is a Pauli limit, but experimentally, we just never see it that killed or even suppressed. We tested it against in-plane field of up to almost 9 Tesla, which is the limit of the magnet. It doesn't get killed. Instead, when you apply a large in-plane magnetic field, it seems that the superconductivity superconducting state occupies a bigger and bigger region on the ND phase diagram. And the TC got enhanced from something like 70 to 95 millikelvin. And the outer plane critical magnetic field also gets strengthened. And that can be seen if you fix the outer plane magnetic field at 15 millitesla without applying an in-plane field, you almost don't see this pair of peaks in differential conductance, differential resistance. But if you apply a 7 Tesla, even with the outer plane field of 15 millitesla, you can identify that feature. That's special for superconductivity. So,
and what do we see on the middle plot?
Middle plot is just a differential resistance as a function of DC current. And this peaks is where you hit the critical current of superconductivity.
And that's for different parallel fields.
That's for different in-plane magnetic fields.
A zero perpendicular field.
Zero perpendicular magnetic field. This one is not so obvious, but if you compare 0 Tesla and 7 Tesla, I think there is a small increase of critical current. Yes?
Does the quarter metal eat into it at all when you apply the field? Like I see it's expanding downward. I can't tell if it's
The quantum metal is actually not expanding.
It's not.
It's moving towards quantum metal.
Oh, okay.
That's the details. We're not exactly sure, but I'll be happy to talk about it. We'll have some calculation. So this superconductivity, although it's very tiny, it's like almost 1 pixel on this map, and you can easily miss it, but seems to be very robust. It survived from 9 Tesla, and that actually corresponds to a huge Pauli limit violation ratio, which is defined as the largest magnetic field that we test divided by the magnetic field corresponding to the Pauli limit, right? Given a TC. So if you put this on the map of all different superconductors, this one actually seems to have the record high Pauli limit violation ratio. Of course, we're benefiting from the fact that the TC here is really low. So with the field Tesla, you are already tens of times beyond the Pauli limit. But that's a way we have to compare different superconductors. Right? And I note that this is just a lower limit because at 7, 8, 9 Tesla, there's no sign of this superconductivity get suppressed at all. Seems to have a long way to go if we manage to apply higher field. Yes.
When you see Pauli limit, you mean the conventional BCS-like stuff.
That's right. Okay, so what we think maybe going on here is that when you apply 0 magnetic field, as we said, the parent state has opposite valley, and the opposite valley are locked to spin, so the spin has an icing configuration like this. And when you apply a bigger and bigger in-plane magnetic field, you are canting the spin directions in both valleys towards the in-plane direction, and you make them to have more and more overlap in the horizontal direction, and that enables the spin polarized component, right? One of the spin triplet part. And you could have icing superconductors like in monomer TMDs. The observation is usually when you apply this bigger and bigger in-plane field, you're suppressing the TC, you're making the superconductivity weaker and weaker. Well, in this case, as I was explaining to you, various test suggests that this superconductivity is actually getting stronger. So that makes us feel like, okay, maybe there is a spin triplet pairing channel that is actually even stronger than the channel that's available at the zero magnitude field, and that allows you to get higher BC or stronger superconductivity. Right? That's a guess based on the phenomena here. That's three-layer graphene. That's rather complicated because I have TMD on both sides, and the SOC plays a role. Next, I'm going to show you a simpler setting. This is whole doping side of 5-layer Rhombohedral graphene, and there's no TMD at all. So there's at most some weak intrinsic spin happening from the carbon itself. So the general phase diagram looks like this. This is a big SC1 that we think is really similar to the SC1 Andrei discovered in tri-layer graphene. And there are a couple of other superconducting states that's in this corner. In fact, you can see an oval here that is what we call as SC2. And again, there's a little single pixel sized thing that you wouldn't be, you can easily miss it. But if you expand it, you actually can tell there are two different states. And this smaller one, SC3, is actually really, really tiny, right? But they're very interesting. So again, I think these features corresponding to whatever is happening on the whole doping side may be associated with the density states. Like I have a little peek at this particular interlayer potential. And it turns out that's not everything that you can get. This is taken at the zero in-plane magnetic field, right? I'm zooming into the range near SC2 and SC3. It turns out if you apply a huge in-plane magnetic field, again, this is like 8 Tesla in-plane magnetic field. You still have SC2 there, you have SC3, a little corner, smaller than at the zero magnetic field. But you've got an entirely new thing that we call as SC4 that was not there at the zero magnetic field. And I have evidence to show instead, in addition to resistivity drop, sometimes it goes to completely zero, sometimes it has a little residue. But all of the superconductivity I've told you so far in this system, SC1, 2, 3, 4, they all have some kind of weak, coherent transport, as can be seen by modulation of the superconductor by the outer plane of the field.
What about the C1 with in-plane field?
I think that one doesn't go beyond the public. I think that's also what's
similar to the trial. Yeah.
So normal state above the TC for say SC4 is a half metal state, or
I think so. I think these are all in the range that you want to get half metal, but with different shape of the fermions. Okay, so these are like different superconductor, and because they all persist to like really high magnetic field, you can tell they are absolutely unconventional in the sense of how many times it breaks the public limit. Right. Well, next I'm going to focus on the SC3, which is the most bizarre looking superconductivity for the following reason. Again, it's very tiny in the ND phase diagram, but when you apply outer plane magnetic field, something really unusual happens, right? This is SC3 at the zero outer plane magnetic field. And when you apply something like 1.8 millitesla, you see this triangle become bigger, right? It's obviously bigger than here. So if you park at the same spot, the same density, the same, actually relative to the bottom here, but there is a little bit shift. But if you look at this state here as a function of the outer plane magnetic field, you see that the superconductivity seems to get strengthened by a single-digit millitesla magnetic field. The critical current is increased by something like 50%, and the superconducting transition temperature goes from something like 60 millikelvin, it goes to 100 millikelvin. And this is single-digit millitesla. So anything that's associated with must be very tiny. either spin Zeeman or valley Zeeman, although valley Zeeman can have a G factor 10 times bigger than spin. So we ask, okay, what can this be, right? You apply some magnetic field, naively, you're coupling to some magnetic moment, and that changes probably the landscape of your parent state, or something like that. And the first thing we test is, oh, can this be, a spin magnetization coupled to the outer plane magnetic field, right? Well, the thing is, this is a very weak spin-off coupling system. So if it's spin dominated, then similar effect should be expected for in-plane magnetic field as well. The spin can couple to both outer plane and in-plane magnetic field. Well, the experiment tells you this enhancement of superconductivity by magnetic field only happens when you point it to the outer plane direction, not in-plane direction. So simply speaking, this enhancement is not a pure spin effect. And then you say, okay, how about its value? Because we're applying outer plane field, it can also couple to that. Well, you can apply similar rationale that if this is pure orbital effect, then when you apply a big DC in-plane magnetic field, that you fix the spin in that in-plane direction, you should expect to see the same enhancement by outer plane field. And that's what we did. We apply a 0.4 Tesla in-plane magnetic field, we scan the outer plane field again, there's no enhancement. It's a monotonic decrease of the critical parameter. So this is also not a pure orbital effect. And then you have only one way out, right? If it's not pure spin, it's not pure value, it has to be pure, something related to spin optical coupling. It has to be somewhat combining both of them, right? So give you the background. In this problem, when you talk about things beyond the single particle level band structure, you have several energy scales. From large to small, you have the Horn's coupling on the order of milli-electron volt for this density range. And this term tends to align the spins from the two valleys in the same direction. Doesn't matter which direction that is, but it tends to align the spin. And the spin optical coupling, so this should be 50 micro eV. Spin optical coupling, this is the intrinsic spin optical coupling, right? Different work estimate is from like 50 to, I think Ali's experiment suggests this maybe 100 micro eV. But that's much smaller than the Horn's coupling. And the weakest is the Zeeman energy, either spin or valley. They are even smaller. Spin at a single digit millitesla is actually sub micro eV, and valley Zeeman is probably on the order of micro eV. The icing spin optical coupling wants the spins in the opposite valley to point in opposite way and lock to the outer plane direction. But the spin Zeeman energy wants to align the spin from the two valley in the same direction, while this time, this field can choose which direction that is, right? Horn's coupling is not really a field because it's happy with whatever direction it is. So you have three energy scales here, and they have a very interesting distribution. From the energy scale, Horn's is the biggest, and spin Zeeman is the smallest, but they share one feature is that they want the spins to be lined up in the same direction. Well, the second energy term, SOC, wants spin to be anti-parallel, and this is obviously much bigger than spin Zeeman energy, but because this third term make an ally with the Horn's coupling, the spin optical coupling effect, the anti-aligned spin effect, is actually very, very weak in this case. As a result, you got the so-called spin canting in such a way that without applying any magnetic field, the K and the K prime value have their spins pretty much all aligned in the in-plane direction, but with a small canting to the outer plane direction to make the SOC energy happy. Okay. And when you apply an external magnetic field, then you can determine which direction the spin Zeeman prefers. And because that's also, Horn's coupling also favors that configuration, essentially you get spin polarized parent state. That's determined, the direction is determined by the direction you apply the external magnetic field, right? And if you apply a small outer plane magnetic field, you pretty much align the value in the two, the spins in two value close to the outer plane direction. And then the SOC would do something that's obvious, that it will create an imbalance between the two values. because now you force the spin to be in the same direction, but SOC will give you a positive energy in one value and negative energy in the other value. You create a value imbalance here. So, based on this picture, you actually can calculate like how the spin polarization of the system and the value imbalance responds to vertical magnetic field. And you find that with the numbers that we can find in literatures, a single digit millitesla outer plane magnetic field actually can finish this tilting, this rotation from in plane to outer plane. And when you apply additional in plane magnetic field, you're going to make this process harder because that's a component that sort of fixes the spin in the in plane direction and it makes the rotation harder to happen. And that will take bigger outer plane magnetic field for to see this spin and the value imbalance to enhance. So experimentally, what we see.
Sorry, kid, I don't feel funny. Have a balance between two much larger energies, Hund and spin orbit,
Yes.
which give you Cantic.
Yes.
Then you apply a very, very small magnetic field. Why you immediately shift spin?
Because Hund prefer that configuration as well, right? All what Hans does is the spin to be parallel. Hans doesn't care about which direction the spin polarized.
Oh, okay, we can talk about that.
So basically, we did the experiment that we check this outer plane field dependence as a function of in-plane magnetic field, right? This is 0, 0.5, 1.0, 1.5, 2.5 millipascal. And as you can see, this enhancement, this slope, as a function of outer plane magnetic field, will gradually decrease as you have bigger and bigger in-plane magnetic field. Although you still get this sort of enhancement of the critical current. And that seems to be aligned with what we expect based on this simple picture. So this kind of answer, of course, like how did you get the superconductivity? But it seems to be suggesting that when you have a value imbalance, this particular superconductivity gets strengthened in TC, or supercurrent. So one possibility that naturally fits in this picture is that if the pairing happens just intra-value, and then when you create an imbalance between the two values, then one of them must get bigger in density states, right? It's not parabolic then. And if the superconductivity TC is pretty much dominated by that value that has bigger density states, then maybe the whole thing shows as a stronger superconductivity. This is not a theory. It's a summary of experimental observations, which makes sense in all the tests that we did. And that gives you a single-digit millitesla enhancement of superconductivity, which is not seen in any other graphene-based superconductor. Okay. And we also went beyond 5 layers, right? We are trying to get into the thicker rhombohedral split layer. And this is a particular case of 15-layer rhombohedral graphene. At the 0 magnetic field, you see some pockets that shows vanishing resistance, but really when you apply some in-plane magnetic field, you see there's like what we call a superconductivity reverse development. This is similar to what Matt was showing you in the morning. This one, I think it goes to 0 resistance, no problem. And Matt would agree with me, that's a real superconductor. And we also checked this corner here. In our data at the 0 in-plane magnetic field, we think this state also goes to 0 resistance. I don't know if this is exactly the same point that you checked, or maybe you checked somewhere here, but at least this point that we checked seems to be, looks like a real superconductor. We can compare it to the data later. Okay, let's take a break. I have only 5 minutes left, but let's take a break here. I've shown you a lot of superconductors in the rhombohedral family, in different layer numbers, different conditions, with, without spherical coupling. And most of them are obviously unconventional in how they respond to magnetic field, right? But if you zoom out from graphene, twisted or crystalline, these superconductors going beyond the Pauli limits, being polarized, or maybe even spin triple superconductor is actually not beyond superconductivity that you observe in other superconductors. Next, I'm going to show you something that's really unique, and that's one of its own kind. And this happens on the electron doped side. Firstly, we got in 4 and 5 layer graphene. And we think in this particular range of displacement field and density, you really got the bottom of the conduction band to be really, really flat. and if you charge into it, you get superconductivity. SC1, SC2, SC3, and 4 layer, and 5 layer. And they have a TC on the order of 200, 300 millikelvin. And sometimes you see this big asymmetry between positive and negative current, which is the so-called superconductivity effect, which suggests time symmetry is broken from theoretical point of view, but I'm going to show you much better evidence of time symmetry breaking. And now we also have it in a 6 layer. This is a collaboration with a previous postdoc Zheng Guang, who is now independent at Florida State University. Made a couple of 6 layer samples, and there's no moraine, no TMD. And he got pretty much the same phase diagram. This is SC1, this is SC2. Because he applied the 50 millitesla in this plot, the SC3 is already killed. SC3 is boring in that sense. And he has a hot bar like this, right? He cannot really pass current in every direction possible, but he can at least check a few directions, right? In this configuration, the current runs from this electrode to this electrode. This direction, in this configuration, it runs horizontally, and in this direction, okay, I didn't show the other. But within this device, no matter which direction we pass the current, we can measure resistance goes to 0, which doesn't seem to have the assumption, right? But the existence of SC1 and SC2 were also reproduced in Leo's experiment. It's just we don't seem to have that isotropy or stripe order superconductivity. And in this case, we actually try to look for the phase coherent transport signature. This is 6-layer graphene, and we drop the pin here. This is SC2. There's something going on, and if you really zoom into between negative and a positive 100 millitesla, which is shown here. If you look at it carefully, there's some very weak modulations, which is actually typical for rhombohedral crystalline graphene, because you just don't have twist angle disorder like you have in the crystal graphene case. Okay, this SC1 and SC2 are very unusual in how they respond to magnetic field. If you apply in-plane magnetic field, SC1 is pretty much still largely there up to 5 Tesla, and this is already beyond Pauli limit by 15 times, and that suggests being polarized. If you apply out-of-plane magnetic field, it's even more bizarre, right? Remember, the TC is only 200 millikelvin. This almost zero resistance persists to something like beyond 1 Tesla. And you apply the simple Ginsburg-Landau estimation of the coherence length. 1 Tesla corresponds to a coherence length of something like 15 nanometer, which is actually already close to the distance, the average distance between 2 charges in the superconducting state, which you can calculate based on the density and draw it as a dashed line here. So at least this SC1 is already in sort of strongly coupled superconductor case. And of course, if you check 4 layer, I think it's more on the BCS side because the critical magnetic field in 4 layers is probably 3 times lower than in 5 layer. And the most bizarre observation we made in this SC1 and SC2 is that they behave as magnets when you apply an out-of-plane magnetic field. It's 0 resistance, tell you it's superconductor, but when you scan the field back and forth, it goes from 0 to finite and back to 0. And when you scan back the magnetic field, it's 0, finite, back to 0. But these 2 peaks has a very obvious delay. If I don't tell you it's a superconductor, you may say, oh, it's a ferromagnetic metal, and it has hysteresis in first one. It's a superconductor. And sometimes you see this temporal fluctuation of resistance, which may be associated with a random flipping of the direction. And this is a unique observation. We think this is related to you have superconducting domains polarized in the K value or K prime value. And when you have a domain wall between them, you detect a finite resistance. Okay? It's stopped or
it's you're going into Q&A.
Okay. And it turns out this hysteretic behavior in transport even persists to above TC. In a normal state, this is a pocket that corresponds to what's going to be SC1 at a lower temperature. So if you look at the star and the square position, you measure the RXY as a function of out-of-plane magnetic field. You have hysteresis, you have jump in RXY. So this is already suggesting the parent state breaks the value symmetry. And even this observation is unique among all superconductors. So we think this is related to the spin and value polarized powder metal and the resistance spike associated with the domain wall and things. You don't have to believe me because Ali is going to show you in the next talk direct evidence of visualization of the magnetic signal in the superconducting state, as well as domain distributions and how they are related to the global transport structure. Okay. So basically, I'm telling you there is a superconductor that seems to be in a spin value polarized pocket. In other words, it's a single flavor superconductor. And because it's quantum metal, spin polarization means it's spin triplet. It cannot be spin singlet or value singlet. The K has bigger momentum, so the Cooper pair has bigger momentum. And most importantly, we call this as a chiral superconductor to emphasize that we break temperature symmetry not only at the spin level, but also at the orbital level. And in a weak spin coupling system like graphene, these two things are separate. That's why in the previous unconventional superconductor I was telling you about, they have spin polarization, but there's no signature of time versus signature breaking at the orbital level. Well, this one does, and this is the only one shows orbital level time versus signature break. And chiral means, not structural chirality. We're not chemists. It's not left and right-handed in structure. Chiral means your Cooper pairs develop orbital motion, and then you can tell the clockwise and the counterclockwise winding, which correspond to opposite angular momentum, opposite magnetic moment. And this is because your parent state already breaks the value symmetry. Right? So in this sense, just knowing the parent state is a spin and value polarized quantum metal, we already know there's orbital level angular momentum, so it's chiral superconductor, regardless of the symmetry of the superconductor order parameter. Of course, you can ask, is this just chiral or is chiral topological? The difference is whether the order parameter is just px or it's p plus or minus ip. If it's a letter, it's topological. At this moment, we don't know. It's dynamic, right? And of course,
weak pairing, right?
I'm sorry?
Should also be of weak pairing.
It should be also weak pairing.
Yeah. If it's a strong pairing, px plus ipy, it would have a chain number 0. No marijuana. So
There's no proof that it's weak pairing.
no, I said it should be.
Okay.
Yes, it cannot be too strongly coupled. Hopefully, we're not in the extreme B limit. The good news is that theorists seem to believe that if your parent state already breaks time versus symmetry, then naturally the symmetry between P plus and P minus IP should be broken. Should be topological, but we have to see what the experiment says, right? And lastly, I want to connect these SC1 and SC2 to a totally different topic, which is fractional quantum unsolved. But there's a good reason I want to mention this. This happens in 5-layer Rhombohedral graphene when you have a moire between graphene and HBN. You get this integer and fractional quantized plateaus at the zero magnetic field. And in the phase diagram, these two phenomena are actually closely related, right? This is a phase diagram with moire. These vertical stripes are integer and fractional quantum anomalous states. Well, this is a phase diagram of 5-layer graphene without moire, and you don't get any of those quantum Hall state, but you get superconductivity, SC1, SC2, right? You take the boundary of this superconductor and you put it on this map, which is a totally different device, but you find that the anomalous Hall region seems to reasonably overlap with the SC1 region when there's no moire. So this tells you that it's the same flap dispersion of the band structure that drives both effects, except for the moire seems to be completely changed the ground state from superconductor to fractional quantum anomalous Hall. But what's essential is you have a flat dispersion in your band structure. Moire is the secondary thing in this whole picture. Of course, specifically for fractional quantum anomalous Hall effect, it's obvious that if you don't have moire, you just don't have that. You don't even have an integer quantum anomalous Hall. but that's specific to that phenomenon. Superconductivity apparently doesn't care about that way. Superconductivity actually disfavored by that way because you don't really see large patterns of superconductivity.
So if you look at the whole resistivity without more above TC, then do you have anomalous Hall effect?
Yes.
So you have a classical anomalous Hall effect,
Yes.
which is not breaking to by more.
But that's a metal. That's not anything positive.
No, of course. Yeah.
Right.
Okay.
We're running way over time.
Okay. So basically, you sort of unify the fractional physics and superconductivity in a very twisted way in this crystalline gravity, and that's it.
Yeah. And thank long. Remaining questions. If there's one more, somebody can ask while we have our next speaker set up.
So did you say that you see a change at 0.1 millitesla or 1 millitesla?
1 millitesla.
Oh, okay. And can you said that this is unique and you can never see one of that. How is this qualitatively different than uranium, germanium 2, or any ferromagnetic superconductor that people have studied?
So in ferromagnetic superconductors, those materials have strong spin-off coupling. So when you get time resistant breaking, they're entangled. You cannot separate. All right. Well, if this is a spin power relation and the orbital magnetism are two separate things, and they have different meanings.
I don't. You have still a 50 milli-electron volt spin orbit coupling, and your TC is not that high. So I don't see.
So we may be talking about different superconducting states.
Yeah. How high is your TC?
I've talked about probably 6 different superconducting states, and I'm guessing that the one you are asking is different from the one that I was answering.
I'm talking about the one you said. I'm trying to understand what is qualitatively different in a ferromagnetic superconductor. Sure, the value of the spin orbit coupling is different, but you cannot break the same symmetry twice. So it's still time reversal symmetry being broken. So
I didn't claim that superconductivity is unique. I said that one is in the category that you have found in other superconductors. Only the Chiral superconductor I talked in the last session is unique.
But that's what I'm asking. What is unique about this?
Because here you clearly have signature of orbital level time resistor symmetry breaking. You have anomalous Hall, you have hysteresis in resistance, and you don't have these in other superconductors.
Why you wouldn't have anomalous Hall in a ferromagnetic metal?
I don't know, but experimentally there's no such kind of thing. But you're really intolerant.
No, I'm talking about uranium germanium too. The ones that
There's no anomalous Hall in any other superconductors, as far as I know.
But again, you broke the same. You're breaking the same symmetries.
Theoretically, I agree with you.
It's not theoretically symmetry.
I'm just speaking from the experimental point of view. I've checked with several superconductor friends working on superconductors. None of us is aware of any experimental data that shows anomalous Hall in other superconductors.
Okay.
Thank long again. Our next speaker is Zeldov. We'll extend the discussion on superconductivity.
It has to show.
I would like to thank the organizers for this meeting. And indeed, I will talk about, I'll continue essentially long stops, and I'll talk about power superconductivity. The work that Whiteman was performed by Jian in larger Jordan in Europe, with close collaboration with Kang, with some theory input from Gal, superconducting electronics from Martin, and HBM results from it. So after a long talk, I can go straight to the point. We want to understand the nature of this pocket, which arises from water metal phase. Has been discovered at MIT, and it has drawn a lot of attention along with it. So we have studied 2 devices.
Is there a microphone?
Microphone. Get one. So we studied devices from long, and that show very similar phase diagram. help me out.
Put it in your pocket.
Good. Is it better?
Yep,
Yeah.
much.
Great. Okay. And if we take a line cut along traces of our XX along this line at different temperatures, we see at our base temperature of 20 millikelvin, we have a zero state resistance, and the TC is about 150 millikelvin. Since for our magnetic imaging, we will need small outer plane magnetic fields. So here are same traces at base temperature, but few low magnetic fields, confirming the zero resistance state. In fact, as Long has shown, the HC2 of this pocket is huge, on the order of 1 Tesla. So the main question is whether this is indeed a chiral superconductor. And for this, we have to be a little more precise about the definition. So a chiral superconductor is a superconducting state with macroscopic time reversal symmetry breaking of orbital nature, as Long mentioned. So our main goal will be first to determine, to provide a thermodynamic proof that actually there is a time reversal symmetry breaking. If chiral superconductivity is indeed established, the next question would be what is the pairing mechanism and whether it's itself a chiral. So if the order parameter, if the system would be described by a single order parameter, these two questions would be redundant. But here the interesting situation is that the superconductivity emerges from a symmetry broken parent state, and therefore we're dealing with multi-component order. So this question boils down essentially to three questions. What is the nature of the pairing state, and which symmetry does it break? Which of these broken symmetries are inherited by the superconductor? And which symmetry breaking is intrinsic to the pairing itself? So this is our schematic experimental setup. At 20 millikelvin, we apply a DC voltage to the top gate to control the overall carrier concentration, and we add a small modulation and measure the corresponding AC modulation in the magnetic field, which is proportional to the differential magnetization dm. We can do the same thing with the backgate, but the important point is that the magnetic signal that we measure is transparent to metals and insulators, so we can see through any structure, including top gates, which allows us to apply a displacement field, which is essential for rhombohedral graphene and specifically for the superconducting state. And we can do simultaneous transport measurements, and we can even modify the magnetization with current. So we start from the quarter metal phase at this green point, and we measure RxY as a function of magnetic field sweeping up and down. And as Long has mentioned, you see an anomalous Hall effect and box-like hysteresis with a recursive field of about 150 millitesla. So now we go to this point at the lower branch, and we do this two-dimensional imaging. So this is the BZA signal, and we see a negative response in the bulk, quite uniform response in the bulk of the sample, except at these two circular regions, which are bubbles in the sample. Now we go to this point on the upper branch and repeat the experiment, and we find very similar distribution, this time positive. And then we can do a numerical inversion and reconstruct the differential magnetization. And we find that it's quite uniform on the order of minus 10 Bohr magnetons per electron here. And in this state, it's the same of the order of 10, plus 10 Bohr magnetons. So obviously, the time reversal symmetry breaking here is associated with orbital magnetization.
Oh, a quick question. Should
Yes.
we take seriously these little tendrils of zero magnetization that go through the sample?
Yes, so these are these 2 points.
No, the little lines.
The wiggles here.
Yes.
Well, it doesn't go to zero, but look here. It's it's everything is these are all nanoteslas, so everything is on the scale of our signal to noise, and there are a lot of fluctuations as we will see afterwards. So ignore this this reconstruction and this wiggles. They're not real. It's just noise. Okay. So this was in the quarter metal at this point. Now let's go to this point in the superconducting phase. And in this is a zero resistance state. So transport cannot tell us whether the system is polarized. So we go to this region, zoom in on the interior part of the sample, and repeat this measurement. So first we apply 150 millitesla, and then go down to 26 millitesla, except that now we are in the zero resistance state, and we find a positive signal. Now, a superconductor, usual superconductor, should be diamagnetic, which would give a blue signal here. So here we see a ferromagnetic state. Now we go to minus 150 millitesla and go down to minus 28 millitesla, and we have a blue negative response. Again, diamagnetism would give us a red. So here again, we have a ferromagnetic state.
Now, look at RXY.
Excuse me?
Did you look at RXY?
RXX and RXY, both of them are zero.
Well, RXY too.
RXY too, yes. And again, it's just, okay. We call it RXX and RXY, but it's not really RXX and RXY, but doesn't matter. To your question, both of them are zero. Yes, okay. Now we go again to positive magnetic field of 120 millitesla and down to 20 millitesla. Again, we see the same state with positive chirality. And now again we go to negative, but this time we come to the positive, exactly the same 20 millitesla, and we have a negative chirality. So here we have two superconducting states, zero resistance, two superconducting states that break time reversal symmetry and have opposite chirality under exactly the same external conditions. The only difference is that this state was trained after positive magnetic field, and this was trained after negative magnetic field. So in summary, we observe macroscopic orbital time reversal symmetry breaking. We image it in real space. We obtain thermodynamic measurement of spontaneous magnetization, and we identify two superconducting states with opposite chirality. So all these provide all the necessary requirements in order to declare a chiral superconductor in this rhombohedral graphene. In fact, this is the first direct thermodynamic observation of a chiral superconducting state in any system, in any material systems that we know. Okay, so once we establish that this is a chiral superconductor, we can look at it more closely. So in fact, this data already tells us two additional important pieces of information. First is that chirality is inherited from the parent state because it shows the same phenomenology. And second is that if we're at the zero resistance state, corresponds to a single domain, as we can see here. So this naturally brings us to the next question: can the two chiralities coexist? So first we do transport studies of hysteresis. So again, we go to the quarter metal phase here, and we see this box-like hysteresis that we have seen before. Now we go to superconducting state in this point, and we find a vastly different hysteresis with the sharp spikes in resistance, as Long has shown. But now we do it more systematically. We do continuously along this blue line. So, and what is plotted here is delta R, the difference between the resistances on sweeping up and sweeping down, as a function of carrier density along this line. So at high densities in the quarter metal phase, we have this box-like hysteresis with a small difference in resistances. This is the light blue color here. And in the superconducting state here, at this density, we see these huge spikes of several kiloohms that you observe here. But interestingly, there is the transition between the box-like hysteresis and the spike-like hysteresis occurs at a pretty sharp specific density below which domain walls proliferate. And if we take this this value of this the density and plot it on our phase diagram, it actually coincides with the onset of superconductivity. We can repeat this experiment at different displacement fields, and we see that the proliferation of domain walls follows accurately the boundary of the superconducting phase. So our conclusion here is that the quantum metal phase has no domain coexistence, whereas the superconducting phase favors the coexistence of domain or proliferation of domain walls.
Question.
Just let me, just 1 second. So as a result, the superconducting phase can expose different resistive states, including zero resistance if we're in a single domain, high resistance here of kiloohms, low resistance in these regions of 10 to hundreds of ohms, or even negative resistance, but I'm afraid I will not have time to describe it. Yes?
Can you see the domains directly in real space?
That's the purpose of the whole talk.
Okay.
Yes?
Is it model? Is the gap isotropic?
Let's come back to this question at the end. I don't think I can answer this question. Okay. So now we repeat the same experiment, but at 1 Kelvin, well above TC. And we see that the quantum metal phase has the same hysteresis, not surprising. Surprisingly, the superconducting region also has the same hysteresis. So these spikes we also observe in the normal state at 1 Kelvin. And so the overall behavior at the base temperature and 1 Kelvin are very similar, and in particular, the density below which the domain walls proliferate remains the same following the same line. So our previous conclusion is wrong. This domain wall proliferation is a property of the parent state, and it is inherited by the superconductor. But the surprising thing is that how come this proliferation of domains at high temperature coincides with onset of superconductivity at low temperature? These should be completely different phenomena. So this suggests that there is some additional phase transition, some additional order parameter, or we call it hidden order, that occurs along this line, which has two effects. One, it promotes superconductivity at low temperatures. And two, it lowers the domain wall energy such that we have proliferation of domain walls both in the normal state, in the parent state, and in the superconducting state. If this is true, it gives an important hint on the superconductivity, namely, it doesn't emerge from a simple quantum metal phase, but it emerges from some multi-component normal state. So now coming to the imaging of the domain walls. So we repeat the same measurement. Again, now we're in the superconducting state, and we go to this low resistance state. And this is what we see. So we find small minority domains within the big majority domain. And if we go to the high resistance state here, we see significantly larger minority domains that encompass several contacts. Now we go to the quantum metal phase, but we want to do it at the same temperature. So we know that this region is a single domain. So we go to this high displacement field quantum metal, where we observe a very similar hysteresis, spike-like hysteresis. So in the low resistance state, we see uniform magnetization except for these bubbles, whereas in the high resistance state, we see a large minority domain with opposite chirality. And if we subtract the two, the low resistance state and the high resistance state, we see actually that in the high resistance state, a minority domain appeared here, separated by a domain wall from the majority chirality here. Since here we are in a normal state, we can just try to solve Ohm's law in a specific geometry, assuming a uniform conductivity. So we just fit the two measured points, the RxX here in the low resistance state and the RxY, and we can extract sigma XX and sigma XY. And this is the corresponding potential distribution driving current between contacts 4 and 2. And this is the corresponding modulus of the current density. And now what we can do, we can just place by hand opposite chirality domain here with the same sigma XX but opposite sigma XY. And we add a domain wall with finite resistance as a tuning parameter to tune these 2 points, the RxX and RxY in the high resistance state, from which we derive domain wall resistance of 41 kilo ohms micron. And so this is a large resistance, and it enforces the current, most of the current to flow in the minority domain and only little current to leak into the majority domain. So according to Landauer, the conductivity through the domain is given by the number of channels per unit length, Kf over pi, times the quantum conductance, times the transmission probability. So we know our Kf from the carrier density. So the 41 kilo ohm translates to a transmission probability of 8 times 10 to the minus 3. So it means that the domain walls are almost opaque to electrons with transmission probability of less than 1%. And this is due to both momentum, the valley mismatch, and the spin mismatch between the two domains. So far we've seen that we can manipulate the domains with magnetic field, with the hysteresis, but actually we can also manipulate them with current. So this is an example in device 2, in the quarter metal phase, in the high D quarter metal phase here. So we see small minority domains here, but once we apply a current of 30 nanoamps, we find a large domain of opposite chirality near contact 1, where the electrons are injected into the sample. This domain expands, inflates as we increase the current, and then when we decrease the current, it deflates and vanishes at zero current. Interestingly, for negative current, there is no minority domain. So this is just a cartoon of what we see here, that we inflate a minority domain by injecting electrons at contact 1. So if the domains expand and shrink rather reproducibly with DC current, they should also respond to an AC current. So here in this example in the chiral, in the superconducting, chiral superconducting phase, with AC current of 5 nanoamps, and we see this blue domain here, and this is a similar example at slightly different conditions where we see 2 domains of opposite colors here. So during the positive half cycle, we inflate a minority domain at contact 1 where we inject electrons, whereas during the negative half cycle, we collapse this domain. And in contrast to here, where the magnetic imaging is done by applying backgate AC modulation, here we don't apply any backgate modulation. Instead, the current, the AC current itself, is the source of the modulation. So at each pixel, our lock-in amplifier actually measures the difference between positive half cycle and negative half cycle. And this is the cartoon of the difference of these 2 pictures. So in this region, the minority domain expands and shrinks during the AC cycle of the current, whereas here nothing happens. And as a result, we have 0 signal here in this blue region here. In this example, we have a bipolar behavior. During the positive half cycle of the current, we inflate a minority domain at contact 1 where the electrons are injected, whereas during the positive half cycle, we create a different domain here near contact 4, and the difference between them are 2 domains that expand and shrink out of phase with each other, and therefore they have opposite colors here. Interestingly, we can see domain wall dynamics at the current of 0.4 nanoamps, which is comparable or lower than currents that are typically used for transport measurements. this has two implications. First of all, transport measurements, instead of being non-invasive, instead of being sort of linear response probe of a stationary system, they're actually invasive, and they dynamically change the domain structure, essentially dissipating the energy. So they're highly sort of, by the fact that you measure the system, you already change it.
So if you measure at some low frequency, shouldn't you expect to get harmonics?
Yes, you are right. In this case, it should be nonlinear, and therefore you should have some harmonics. You are right.
So this is probably something you can check.
Well, the signals are extremely. I mean, you are measuring zero resistance state if you want. So obviously, the higher harmonics will also be zero, but the dissipation is extremely small. In principle, you are right. We haven't tried this. Well, we did something similar, but I will not go into it. But at larger count. So as I said, one conclusion is that one has to be careful because transport itself is no longer a sort of innocent probe. And second is that in contrast to the quarter-metal phase here, where you can think of the system as sort of rigid in the sense of symmetry breaking, this entire region to the left of this line behaves like a very soft and malleable, if you want, system where small currents can change it significantly. And this is the result of two facts. First is that the domain wall energy is low in this part, which means that the pinning is also very low. And second is that the domain walls are opaque, which provides a very efficient mechanism for linear momentum transfer between the current and the domain wall. Since, as I said, the system is soft in this sense, in sense of coexisting of domains, one can actually create a very low power, ultra low power resistance switching. So what we do, we apply a DC current of 1.7 nanoamps or minus 1 plus minus 1.7. We switch between them every 40 seconds. And in parallel, we measure the resistance, or X and Y resistances, using an AC current of 1 nanoamp. So when the DC current is negative, we are in the low resistance state with RxX close to 0 and RxY a few hundred ohms. Whereas when we apply a plus 1.7 nanoamp, the system switches to a high resistance state with RxX and RxY on the order of 2.5 kilo. So these are one of the lowest switching currents ever reported in the literature, orders of magnitude lower than typical milliamp currents for spintronic devices. So here we image these two, the low resistance and high resistance states. So in the low resistance, in both cases, we see such blobs, such domains. In this case, we've trained the system with negative magnetic field and then went to positive. So the majority domain is K prime down. And the negative current injects electrons at contact 4 and therefore stabilizes a minority domain here. During the negative half cycle, this domain expands because more electrons are injected here. And the difference between the two is this cartoon, which reflects what we observe experimentally. For the positive current, this minority domain is narrower, but expands over two contacts, 3 and 4. And during the negative half cycle, it expands, and the difference looks like this as we observe in experiment. So again, it shows that the low resistance state, we have small domains, localized domains, whereas in the high resistance state, the domains span multiple contacts with the domain wall between them, resulting in these huge resistances of kiloohms. But again, what I want to emphasize here, that the signal that we measure, or the size of the domains that we measure, reflects by how much the domain walls move or expand or shrink due to the small AC current that we use for measurement. And you see that they expand dramatically. So that the 1 nanoampere is a standard current that people use in transport measurements in 2D materials, and it creates a very large the displacement of the domain walls. So again, it's invasive and no, yes.
Can you go? So just to understand the numbers again, you have plus minus 1.7 nanoamp, and you have 1 nanoamp.
Yes, which is slightly lower than the 1.7 intentionally. So
only so the two are comparable.
The two are comparable, yes.
So basically, you measure with a 2.7 for half of the time, or the 0.7
correct
the other half of the time, but you don't get the same result that you would have gotten if you measured 2.7 for half an hour and minus 0.7 for half an hour.
Absolutely.
This is the message.
Yes.
Okay. Thank you.
And if you want, it's a very nonlinear system.
Yeah.
Okay. Definitely. Okay. Another aspect. Okay, thank you. Another aspect of the softness of the system is stochastic behavior. So here are two examples of where we see during our imaging domains change. So in order to understand, and as Long has shown, and it has been often see, when you do transport, you see streaks in these regions and spikes and so on. So in order to understand that, we simultaneously measured the imaging and measured transport. So these are RxX and RxY values measured globally as a function of time, but we just render them in this way to correlate with the position of our squid on tip. So we start scanning here, and we scan along the horizontal lines. And in the first few lines, RxX and RxY are more or less constant. But then when we go to this line, at this point, both RxX jump suddenly and RxY, which exactly coincides with the change in the domain structure, in this case, from this blue to red. Now we go to 150 millikelvin above TC, and we see same behavior even more promptly. As you see, the resistance changes abruptly here in close correspondence to the complete change of the domain structure in the material. So this shows that this stochastic behavior is again inherited from the parent state. And another example is that we go to the superconducting state, for example, here, and just watch RxX over 3 hours. So what you see very large fluctuations. And if you zoom in here, you see that the system starts from a zero resistance state with occasionally very short time jumps into the high resistance state. And then after 22 minutes or so, it jumps into the low resistance state and stays there for 3 hours with occasional jumps towards the zero resistance state. So again, this fluctuating superconducting state is a result of low domain wall energy, which is inherited from the parent state. Let me come briefly to the question of the opaque domain wall. So in order to understand the origin of this, again, we do this hysteresis measurements, and we record the maximum value of RxX. So in this case, it's about 6.5 kiloohm, as you can see here. But now we apply an in-plane magnetic field of 50 millitesla, and we see that these peaks decrease, same for minus 50 millitesla. So the average in this case is about 3.5 kiloohm. And if we apply even 500 and minus 500 millitesla in plane, we go down lower, and this is the rest of the points. So we see that the RxX decreases monotonically with in-plane magnetic field up to about 0.1 Tesla, and then saturates at some value. So this tells us that actually both spin and valley mismatch between the opposite chiralities contribute to the domain wall resistance, whereas when we go to high in-plane magnetic field, we align the spins in the opposite chirality domains, and we are left only with a valley mismatch. So this tells us few important insights. First is that opposite chirality domains are associated with opposite isospin, not just opposite valley. A second is that contribution of valley and spin mismatch to the transmission probability is comparable, because as you can see, the saturating valley here, close to 3 kiloohm, is about half of what we have here. And another important point is that in none of the cases we observe any Josephson coupling between the opposite chirality domains, which I believe gives us an important hint about the pairing symmetry, which hints to the fact that also the pairing symmetry is different. For example, if it's chiral, it would further suppress the Josephson coupling across the domains. So let me just summarize. So we establish that we have a chiral superconductor in the rhombohedral 5-layer graphene through thermodynamic measurements. We conclude that the superconducting order parameter is essentially multi-component, part of it coming from the parent state, including the chirality that is inherited. An important understanding is that something happens along this line in the parent state. So the superconducting does not emerge from a simple quarter metal, but some additional order or some additional symmetry breaking occurs here, which assists in both the formation of the superconducting state and in this softness. So in this region, the symmetry breaking is very rigid, and the system wants to be either in one chirality or the other, whereas to the left of this line, it accommodates very easily opposite chirality. We observe in real space the coexistence of opposite chirality domains. We conclude that the domain was highly opaque, and there is no Josephson coupling across them. Within the superconducting state itself can show finite resistance. Maybe it is related to what Matt has been showing, although it's a very different system. So again, if we are in the superconducting state itself, we can be either in the zero resistance state or very high resistance state or this low resistance state here, or even negative resistance, just because you have multiple domains and the domain boundaries are highly resistive. So you can have any mixture essentially as you want. We can easily, by applying a current, we can easily reconfigure the superconducting state and the domain structure, including ultra low current switching between low resistance and high resistance states. And finally, for similar reasons, there are a lot of fluctuation in this system with random domain flipping and this stochasticity, as I've mentioned. Thank you very much for your attention.
Questions?
Two questions about the same. Hidden order.
Yeah.
First experimental question. You showed the data for 1 Kelvin, I guess. Did you try to go to higher temperature to see whether this, what you call hidden order, survives up to certain temperature?
Yes, we have not done it systematically. Perhaps Long can answer the spike features up to what temperature they persist. We should do it more systematically.
I don't have it off the top of my head.
Okay, and second question about the same. Can it be something more simple, that there is no hidden order? Sorry. But as you go from one corner to another, from what you call rigid to soft, there are just more fluctuations. You approach the boundary of, say, quarter metal state, there are stronger fluctuations, and you have
the quarter metal state extends up. Half metal is somewhere far away. So
no, I'm not talking about half metal. I'm talking about the boundary between, say, quarter metal and full metal.
No, the full metal is up here and at much higher sort of. So all this is presumably quarter metal.
So what happens if you go further to the upper left.
What? Larger displacement field?
Larger displacement
and
field.
smaller carrier densities. So again, from what we know from quantum oscillations and so on, so the problem is that you cannot tell exactly what happens here because you lose quantum oscillations here. So quantum oscillations are very clear here. So you have quarter metal, then you have half metal, and then you have full metal. And there is no well-known additional symmetry breaking that happen. Of course, fermiology can change a lot. You can have here some trigonal warping and so on. So we believe that this is somewhere here in this region. You go from single Fermi surface to annular Fermi surface. Okay, but exactly where is it? It's not clear. But simple fermiology, it would be very strange to why these two phenomena of rigidity, if you want, of your chiral symmetry and the superconductivity coincide so closely with each other. So it looks that it has to be something that promotes superconductivity and also somehow makes the two chiralities closer in some sense, that the domain wall separating them has a smaller barrier. Should I do the chairman work? Okay, sure. Yes.
I think so. Could you explain the why if these domain walls are so opaque, what is the mechanism for not having Josephson coupling?
Why there is no Josephson coupling? So if it would be a usual superconductor, so we believe the domain walls are atomically sharp on the order because they have to go from K to K prime, right, which is K of the order of a unit cell, right? So we believe that the domain walls are pretty sharp, and it's very surprising that you don't have Josephson coupling across them.
So why?
Well, that's why I'm talking to you guys. Yes. Andrei? Yes.
I think this is related to Andrei's question. Basically, what they expect if I don't low density,
right?
At one electron, it's not going to polarize value.
That's right.
So I just tune in a little bit of it's going to be the polarization is going to be soft, right? So I would totally expect such a soft to rigid.
Oh yes, that's fine. But why does it coexist?
At flat bands, I'm just polarizing spin and value. But at low density, it's going to be.
But is it sharp, or is there really something sharp about the stiffness of the domain wall?
Well, you tell me. You see, you have and there is another point that I forgot to mention. Okay, so again, here you have this simple, let's call it rigid symmetry breaking. So the system wants to be either in one state, chirality, or the other. You don't have any domain coexistence. And here the spikes, both local measurements and global measurements, tell you that you have domains, opposite chirality domains present. And you see that you go quite sharply from one type of hysteresis with no domain walls to another one. And this point is, these points are plotted here. Okay. So, and this you can do at 1 Kelvin. And the question is why this coincidence coincides with onset of superconductivity at 100 millikelvin. So there must be some mechanism that does both.
And it's really sharp boundary.
Well, sharp is it's a matter of your eye. This is quite sharp to me. Yes.
You isolate quite big this chirality domain, and then, for example, to probe it with a Raman, just to see some Raman circle diagram also.
Raman probing what? What do you want to probe with Raman?
The chirality, but since you have different domains.
But here we have a thermodynamic measurement of the chirality.
Yes.
Right. So we have spontaneous orbital magnetization that we image directly. So this is the strongest probe that you could have imagined to prove time reversal symmetry breaking, which it's a thermodynamic probe.
Patrick, if I do a cut across this pink line across this
Can you speak up?
If you imagine doing a cut across this pink line. So where you go from these rigid domain walls to these less rigid ones, does the magnetization in the polarized state change
Okay.
quantitatively?
Yes, I understand your question. Okay. So the orbital magnetization changes dramatically as you go from. So somewhere here you have a half metal to quarter metal. At the transition, the orbital magnetization is largest, and it goes down monotonically on a single particle level. If you do naive calculation, eventually the orbital magnetization should go to zero. This is what Long has shown this movie of the Berry curvature. So in this region, we're supposedly in this region that Long has shown with highest density of states and flattest band. So the flat bands, the flat part has essentially zero Berry curvature and zero orbital magnetization.
I meant experimentally. The orbital magnetization that you measure, do you also see a sharp transition in that?
Sharp transition, no.
That orbital magnetization is continuous when you go across the
right. So we don't see within our resolution, we don't see a contrast in the orbital magnetization to the right and left of this line, if this was your question.
Yeah, thank you.
So,
yes.
Eddie, sorry to try to correct this, but the statement that the flat bottom has zero Berry curvature is incorrect. It doesn't have zero Berry curvature. It has a Berry curvature that's VF over T perp squared. It's constant.
It's constant and it's small.
Well, depends what you mean by small. If you integrate it up to the rim, it's
no, the rim is above it. So at the rim you have Berry curvature,
No. This is a well-known problem. If you do it from the 2x2 model, you're going to get zero. But if you don't do from 2x2 model, it's just the wrong thing to do because the wave functions have their own Berry curvature. It's VF over T perp squared, and it's a thing that's been propagated in talks.
Okay, so this is. I understand what you are saying, but when you do the calculation, it looks quite different. So this is the calculation of the self-rotation part of the orbital magnetization as a function of carrier density and displacement field. And you see here it's very large, like 12 Bohr magnetons, and it goes essentially almost to zero, not to zero, complete zero, but it becomes very small in this part. So this is to your question. So experimentally, we see it very clearly that the orbital magnetization continuously goes down, and this is where the highest density of states is, and this is where the orbital magnetization per electron is smallest. Integrated, we know what it is, 0.6 pi up to the rim, okay? But if you didn't have this Berry curvature in the flat part, you wouldn't have any difference between up and down. No, of course. Well, but you have to be careful. You can have...
It's not zero.
Okay.
And this is the only thing that makes this difference.
Okay, so if you look at on the whole side,
we can continue the discussion.
Actually, the orbital magnetization changes sign. In the annular part, it's of opposite sign than outside the rim.
So, I'm talking about the annular part. I'm talking about flat part that long.
Yes. Okay, but it's much smaller than at both sides. This is a trivial calculation, okay, that is shown here.
Orbital magnetization is much
let's think.
So the Berry curvature and orbital magnetization are not the same thing, right? So
it's zero.
Thank you, speaker again. Minutes. So we will leave our meeting at 4:35.
Thank you. I'm fine.
Yes.
You know about conventional fitting position for that?
That's what it started. Next speaker is Devakul.
All right. Yeah, so thanks for organizing this great workshop. So today I'm going to tell you more about rhombohedral graphene, and specifically this particular rhombohedral graphene experiment that came out a couple years ago that surprisingly we haven't had too many talks about, but it's this pentalayer, but there's a moire, so it's different from the previous few talks. There's a moire with HBN on one side, and this was the sort of experiment that got everyone interested in this system. So this is from Longju, and they see these integer and fractional quantum anomalous Hall effects along this strip of high density of states, and there's sort of been a massive amount of theoretical activity on this topic, a lot of which by people sitting in this room. And I guess I'm not going to have time to review all that's been done, but I guess the main outcome of a lot of this theory is that even this Chern 1 insulator is not just another Chern insulator. And now in the era of Moire, we have sort of too many Chern insulators to count, but this one is still manages to be unique. And in this talk, I'm going to talk about how we think there's actually quite a lot of interesting sort of non-equilibrium physics that's hidden in this phase diagram. Okay, so to explain that, let me first talk about something completely different, and that's skyrmions. So this is a picture of a skyrmion. A skyrmion is just a topological texture in some continuum spin field. And these are actually quite well studied in the context of magnetic materials. So they like to form lattices. So this is a real, on the left is a real experimental image measuring sort of the in-plane spin in a magnetic field of one of these skyrmion materials. And you can see there are skyrmions. They like to form lattices. On the right is an artist's rendition of what this looks like. And in the skyrmion literature, there's actually quite a lot of interesting phenomena that people identified. So people are actually trying to use skyrmions to do like actual skyrmionics. I don't know how promising that is, but there are some interesting phenomena. The first is this so-called topological Hall effect, where if you have a skyrmion that's sort of pinned in place and you try to move an electron on top of it, the fact that you have the spatially varying spin field means that if the electron is trying to locally align its spin to the background skyrmion texture, it essentially picks up a Berry phase term from this background spin texture, and that is felt by the electron as a magnetic field, just through the Aharonov-Bohm effect, basically. And that's what people call this topological Hall effect. If the skyrmion is not pinned, then you can drive a current, and the skyrmion actually moves in response to that current. In the skyrmion literature, people also look a lot at these collective excitations of these skyrmions. So they're not really rigid; they're sort of spontaneously formed textures, and so they can sort of oscillate about their ground state position. And there are a whole bunch of collective modes that people have looked at. There's sort of these clockwise and these counterclockwise modes. There's breathing modes where the skyrmions sort of getting bigger and smaller, and all these higher order multipolar modes. Okay, so why did I talk about that? So in this talk, I'm going to make the case that this Chern insulator in rhombohedral pentalayer graphene moire superlattices can be very naturally viewed as a pinned skyrmion lattice, and not just a ground state. This system has sort of all the dynamics that you expect from real, sort of an analogy with a real skyrmion, magnetic skyrmion system. And I'm going to do this roughly in 3 parts. First, I'll just show you, I'll give some numerical evidence that this thing that the ground state can be understood as a skyrmion lattice. Second, I'll try to explain why based on some recent theory that we have. And third, I will discuss some sort of natural experimental predictions that come out of this picture. Okay, so the first question that I should answer is what this is a skyrmion texture, but in what? So in this Chern insulator arises from basically what you can think of as a spin and valley polarized state. So we can just ignore real spin and valley. And so the remaining sort of pseudo spin degree freedom we have is layer and sublattice. So formally, what I'm talking about is a skyrmion texture in this, I guess, 10 component, if you include all the layers and sublattice spinner. But for all practical purposes, the weight of the wave function is basically mostly on just the top few layers polarized by this strong displacement field that is in the experiment. And so for visualization purposes, this is great because we know how to visualize a 2-component spinner. We can just put it onto a block sphere where basically the north and the south pole correspond to the topmost being fully polarized in the top and the secondmost layer. So that's the setup. And now let's just look at the Hartree-Fock ground state. So many people in this room have done Hartree-Fock on this system. And here, all I'm plotting on the left is the top layer charge density and the second layer charge density. And on the left, you can see that there is sort of a honeycomb shape charge density on the top layer. There's a minimum at 0 where it almost goes to where charge density almost goes to 0. And right at the origin, where that minimum is, there's a peak in the second layer charge density. So I want to motivate that this structure is essentially what you expect from a skyrmion that looks like this. So in the very middle, it's sort of pointed straight down. It's only on the second layer. And on the outside, it's sort of pointed out. It's mostly on the top layer. OK. We can make this more precise by directly calculating some skyrmion density. So from the Hartree-Fock ground state, what we can do is we can calculate this local density matrix indexed by all the sublattice and layer degrees of freedom. And this density matrix will have some eigenvalues. And it turns out there's always sort of a biggest eigenvalue. And the eigenvector corresponding to that now defines a sort of texture in this n-component spinner space that varies with space, with position. And from that, we can define a skyrmion density. So there's a formula for it. You take this eigenvector, you take the outer product, and then you calculate this density. And that is shown here for the Hartree-Fock state. And what you see is it's mostly 0 everywhere. And then there are these sharp peaks right at the middle of the unit cell. And integrating the density over this peak gives you 1. So as you expect, or as I want to, this sort of is evidence that there is essentially a skyrmion per unit cell right where you would expect from the last slide. We can also look at the collective modes. So, oh, yes.
So this is already in the presence of moire due
Yes.
to HBN, right?
Yes.
And at filling factor 1.
1.
Is there any symmetry that's broken that's not already broken because you're in a valley and spin?
You mean by the skyrmion state?
Yeah.
No. Okay, so we can also look at the collective excitations. So this is we just take that Hartree-Fock state that we had before. We do time-dependent Hartree-Fock. That gives you what you can think of as the Magnon spectrum of this system. It looks like a mess, but there are a few low-lying bands that are isolated, and we can look at what these things look like. So we can look at the gamma point and basically look at the top layer charge density which I argued the minima in this charge density is sort of where the Skyrmion cores are, and plot that as a function of time in this calculation. And what that shows you is that this middle one, this lowest one, you can think of as just basically some kind of phonon-like mode where all the Skyrmions are going clockwise. The next one, they're going counterclockwise. And then here we have, if you sort of look at near the minimum, this thing is no longer a circle, it's sort of an oval, and this oval is rotating in time. And so that is a some multipolar excitation. And here you can see the same thing, except it's becoming a triangular. That's an m equals to 3 state. And if you go even further, this other one, you can, if you look at this, this is kind of like a breathing mode where the Skyrmions are getting bigger and smaller as a function of time. And that was only at one particular value in the point in the parameter space. This phenomena is pretty robust across the parameter range when you do see the Chern insulator as your Hartree-Fock ground state. So here we're staying at n equals to 1 and just changing the displacement field. And other people have calculated this before. Eves was the first one to calculate this as far as I'm aware of, and they also see some low-lying modes. And those low-lying modes are essentially these phonon-like and these multipolar Skyrmion modes. And for comparison, this is the plot I showed earlier of magnetic Skyrmions, and you can see there's almost a one-to-one correspondence between these modes of rhombohedral graphene and the magnetic Skyrmions. Okay. So far I've just shown some numerical evidence of what the ground state looks like. The natural question is, why? Why should this system have Skyrmions in the ground state? And it all comes down to basically sort of the unique quantum geometry of this conduction band in rhombohedral graphene that we've seen multiple times, combined with interaction. So it turns out it's a short-range electron-electron interaction that's crucial. And these two ingredients, it turns out, is sufficient to sort of very strongly favor the formation of pseudospin Skyrmions. We make this statement precise, and sort of we can prove various statements via some exactly solvable ideal limit of the system. And then the role of the moire is basically to sort of hold this Skyrmion lattice in place so that you can get it can serve as a background for electrons to form a quantum Hall-like states and Chern insulators and so forth. So let me very briefly give a summary of what we actually did in terms of theory. So we looked at this. Yes.
If there wasn't a moire, there would still be a Skyrmion lattice commensurate with the density or something.
It depends on the model that you're considering. It's if you do Hartree-Fock enforcing the periodicity, then yeah.
Go ahead. Sorry.
Yeah. So it depends on the model you're considering. So we have models where it does sort of you do Hartree-Fock, you find the lowest ground state is basically this anomalous Hall crystal state that people found all the way from the very beginning. But yeah, it's very model dependent.
And that's a Hartree-Fock statement.
That is a Hartree-Fock statement.
So,
yeah.
What's the difference between models when you have it or you don't have it?
So for real rhombohedral graphene, as I'll get to, the moire is actually if you don't have the moire, I'll talk about that at the very end. Yes.
There's a beyond Hartree-Fock statement, right? Which is that the Hartree-Fock statement is that the Skyrmions crystallize, but there's a beyond Hartree-Fock statement that they form, but they could be in a liquid instead of
right.
But that statement.
So that statement is in the ideal limit.
Yeah, in the ideal limits, an exact statement that they form.
So I will briefly give a flavor of that.
In the next slide.
Yeah. Okay. So what is the ideal limit? So there's a small modification to the Hamiltonian that we can make. The precise modification is not too important, but the precise features are the following. So in the real model, rhombohedral graphene has this dispersive band with flat bottom, as we've seen. In the ideal limit, I want this band to be completely flat so that I can ignore the dispersion. But also, I need to have some special structure in the Okay, so that's the first feature. The dispersion is very flat. This band in this limit is perfectly sublattice polarized. It's all on the A sublattice, let's say. And it's also analytic in kx plus iky. So basically, the wave function is basically this thing in layer space. It's all sublattice polarized, so it's sort of 1, and then k squared, k cubed, and k fourth. And this is a pretty good approximation to the real spinner as you get very close to k equals to 0. As you get further away, it becomes more different. That's why, you know, this is a Berry curvature. It doesn't look exactly the same, but it's very qualitatively similar. You get this ring, and at small k, it agrees very well. And on top of this, we have a final ingredient, and that's short-range interactions. Specifically, we want very, very sort of contact interactions, basically, delta functions in position. And this is a density-density interaction.
Why this function is fully holomorphic in K?
So you mean why?
In K, in complex K.
Yes.
You wrote a holomorphic function.
Yes.
Why is it?
It's just due to the Dirac Hamiltonian has a kx plus iky in the off diagonals. So every time you sort of go from one layer to another layer, you sort of pick up an extra factor of kx plus iky. But it's just a Hamiltonian gives you this.
You can have wave function which also have anti-holomorphic components, right?
Yes, yes. Well, in the other valley, it would be anti-holomorphic.
But what's special about this one? Is it a ground state, or what is it?
This is just the single particle block state of this flat band. So if you change it something, you won't be in this flat band anymore. Okay. And I'm going to basically project to just this flat band in my next, once I add these interactions. Okay. So in the ideal limit, let me just flash some statements that we can make. So again, our Hamiltonian is this flat band Hamiltonian, goes off to infinity. So, you know, strictly speaking, this is not a well regularized model. K goes off to infinity without constant kinetic energy. And that's something that we'll have to deal with later by adding back in some kinetic energy. But that's our Hamiltonian. And it turns out that we can basically prove some statements in this limit. So one statement we can prove is that this Hamiltonian has exact zero energy Slater determinant ground states.
The electrons are spinless?
The electrons have a layer spinner. They're spinless, though, real spinless. Yeah. Okay, so first of all, the fact that there are exact zero energy ground states is not true in general for this, even with the delta function interactions. But because of the holomorphicity property, it is true for the system. And we can also prove that if they're Slater determinants, they all have to be basically of this form, where it's basically some lowest Landau level determinant multiplied by, basically, you can think of this chi as some layer spinner. So it's indexed by L. L here is the layer index of particle I. And this is basically a layer spinner field. So all particles have the same factor. And what that tells you is that every electron in the system is always aligned with some local layer spinner texture given by this chi. And in order for this thing to be an exact zero energy ground state, chi has to satisfy these following rules. So on the top layer, chi zero can be chosen to be anything. But all the subsequent layers, chi sub L, are all related to chi zero by some differential relation. And this just follows from basically looking at this wave function and saying that has to be a zero energy ground state of Hamiltonian. Okay, and we can also prove that if we further want this state to be periodic in space, then chi L must describe a Skyrmion lattice with one or more Skyrmions per unit cell. Okay. So I have a few more comments about this ideal limit Skyrmion lattice. So it describes a state in which all electrons are perfectly aligned to a real space texture. That's kind of non-trivial when you compare it to like other Skyrmion systems, like where usually the starting point is you have a band that has some spin degeneracy, like a spin up and a spin down band, and then you sort of try to align it in real space. But here your starting point is a band where the layer spinner is already aligned to momentum space, and you somehow want to simultaneously align it in real space. That's generally not possible, but with this holomorphicity, it turns out that we can satisfy both properties sort of simultaneously. And in this limit, we have no dispersion. And one consequence of that is that the Skyrmion texture can really fluctuate completely freely. Like we can choose this chi0, which just determines where the Skyrmions are completely freely. So it sort of fluctuates however it wants, and it costs zero energy. So really, there's sort of an infinite manifold of degenerate ground states that are Slayer determinants. And you can, of course, make sums of those which are no longer Slayer determinants. OK, so with dispersion, so we can take this flat band, we can sort of regularize it by adding some k-squared dispersion on top just by hand. OK, well, first of all, we can no longer make many exact statements. Once we add dispersion, it sort of ruins any sort of exact statements we can make. But one way of understanding what it will do, at least when you try to think of it sort of restricting to the space of Slayer determinants, is that with dispersion, it'll sort of pick out the lowest energy Skyrmion texture. In this case, we actually almost know exactly what this is. This chi0 should be like the lowest Landau level wave function at some block wave function at some momentum q, complex conjugated. That's not too important. But also, once you've picked out the lowest energy Skyrmion texture, you can sort of now look at collective excitations about that, and we can understand that analytically in this limit as well. And finally, all of the physics that, or at least a lot of the physics that I'll be talking about in this ideal limit can be adiabatically connected to the Hartree-Fock ground state of real rhombohedral graphene. So I will explain a bit more about these last 2 points now. So let's look at the collective excitations in the ideal limit. So we can address this using the time-dependent variational principle, which basically, let me go a bit faster. It's basically the variational principle applied to the action with respect to time-dependent wave function. And we're looking at basically frequencies of small harmonic oscillations about some steady state where delta S is 0. And this plot has a lot in it, so let me explain each curve individually. So the crosses is the result of time-dependent Hartree-Fock done for this ideal limit. So we just take the ideal limit, we add dispersion, and then we do Hartree-Fock and TDHF on top of that, and we get these blue crosses. So this is time-dependent variational principle in the space of Slayer determinants. We also can do something more clever, given that we know what the wave function should look like. We can do what we call chi TDVP, which is basically a time-dependent variational principle, but you basically allow only fluctuations of the Skyrmion texture, only of chi0. And that gives you this blue line that basically crosses through all of the blue crosses. So basically, all of these excitations are pure excitations of the Skyrmion component of the wave function. And finally, there's these red lines, which is some kind of single mode approximation where we, I told you that the Skyrmion chi0 is given by this lowest Landau level wave function. We can sort of add in a small component of an nth Landau level wave function and shift it by some momentum q. And that gives you this red line. And you can see that for the higher ones, it agrees pretty well. For the lower ones, it sort of misses this gapless mode. Here we have no more array, so this is a Goldstone mode. But that's missed by the single mode approximation. So in this ideal limit, we have sort of this tower of collective modes that you can label by an integer. And each of these can be understood analytically. So if we look near the Skyrmion cores, for instance, and look at the nth mode for n greater than or equal to 2, you can see what the shape of the Skyrmion is doing. And it basically looks like something like this, where you basically have an n-fold deformation of the Skyrmion shape. And this thing is sort of rotating chirally with time. So these are basically some plots of the top layer charge density. These are basically the Skyrmion multipolar shape modes that we saw in real pentalayer. But here in the ideal limit, you sort of have infinitely many of them, n goes off to infinity. In reality, only the n equals to 2 and the 3 one survives. Oops. Okay, ignore this thing, but let me now just address the adiabatic continuity. So we can look at this Hamiltonian where we sort of interpolate from the real to the ideal spinor structure. So that's all the difference between these two Hamiltonians, is that the spinor structure is changing. The ideal limit here has dispersion that's created to match the real one. Then there's the Moiré, and then Coulomb, and then we can also add contact interactions on top of that. So when lambda goes from 0 to 1, you're tuning from real to ideal spinor. And as V0 is increased, you can sort of increase the contact interaction relative to everything else. And so this ideal limit sort of corresponds to the limit to the case where lambda is 1, and V naught is sort of very, very large compared to kinetic energy and all the other terms in the Hamiltonian. And what I'm showing here is the sort of the momentum distribution function, n of k. So the real rhombohedral graphene is this line. It's kind of hard to follow, but when we go from lambda 0 to 1, the momentum distribution function is now this red dots, which is pretty much almost indistinguishable from lambda equals to 0. So not much is changing as you tune lambda from 0 to 1. And then as we increase V naught, it sort of gets broader in momentum. And eventually it'll approach this blue line, which is our lowest Landau level, simplest Skyrmion ansatz that should hold in this limit where V naught is infinite. We can also look at this trace condition, which is the difference between the trace of the quantum metric and the Berry curvature. And as you sort of go in this limit, you turn V naught up, this band, this Hartree-Fock band, basically. So this is all just Hartree-Fock. The Hartree-Fock band basically becomes ideal. So this is a limit where this rhombohedral graphene has this trace going to 0. Okay, that's it for the ideal limit. Now let me come back to real rhombohedral, and let me discuss some experimental consequences and some predictions of this. So first, I guess we have these collective modes. They're on the few tens of MeV scale. What are promising routes to measuring them? Let me just go through this fairly quickly. So we have all these modes are basically fluctuations of the layer spinor. And so they are accompanied by charge movement, either in plane or in the out of plane direction. And so they should couple to electric fields in various directions. The higher order ones have high angular momentum, so they're going to require some higher order processes to couple to. Let me just mention a few. I think that some of these on-chip terahertz techniques might be able to detect some of these. There was also some recent experiment using circular polarized Raman to measure the spin 2 mode in fractional quantum Hall systems, this chiral graviton mode. And so the same method should also, this is an angular momentum 2 object. The quadrupolar mode here is also an angular momentum 2 object. It should couple, it should also be probable by this method, but I would love to talk to experimentalists more about this. But I think sort of another very interesting prediction that this Skyrmion picture makes is that it raises the possibility of this a new kind of charged quasi-particle, which is the Skyrmion vacancy. So we considered this setup. So we have rhombohedral. There's a Moiré with HBN, and then deep in the HBN, usually we take like 10 nanometers or something. We put a defect, and this defect is negatively charged. There's a common type of defect that can occur in HBN. And now we can do Hartree-Fock without enforcing Moiré scale periodicity. So we take a torus. We take L by L torus. Here L is 6. And then we do Hartree-Fock, but with one hole doped in. So we do n equals to L squared minus 1. And here I'm just plotting the Skyrmion density. And the defect is right in the middle. And basically, you have a lattice of Skyrmions, and right in the middle, you're missing a Skyrmion. If you look at the top layer charge density, the minimum that used to correspond to a Skyrmion is just missing right in the middle. And you can sort of look at the change in the electron density relative to the nu close to 1 state, and you get this weird pattern where actually in the very middle, your total charge density is increased, but then sort of in the halo surrounding it, your charge density is decreased, such that the integral has to be -1, because this is one hole. So it sort of has this halo shape that, yeah, and the fact that the Skyrmion vacancy carries a charge of one hole is sort of expected from this quantum Hall analogy, since at nu equals to 1, you basically have 1 electron per magnetic flux. Getting rid of one of these Skyrmions is like getting rid of 1 magnetic flux for the quantum Hall state. Okay, right. So this is, I think, sharp experimental signature. If you go to nu equals to 1, and you sort of have this nice uniform lattice, then at nu equals to 1 minus x, where x is very small, sort of if your hole gets localized by some defect, it should appear as actually a missing minimum in the charge, which I think is a pretty sharp sharp signal. And yes, okay, and I think that if these are really the lowest energy charge excitations, which our numerics seem to suggest, then these should probably mediate charge transport at nu equals to 1 minus x as well. I guess the big question that I don't have an answer to yet is, what is the sharpness signature of this quasi-particle that doesn't require STM imaging, which is very hard for the system? Let me know if anyone has any ideas. Okay, now let me come back to this question about moire. So there are a couple of technical comments that I found very interesting when we were modeling this Skyrmion vacancy. First, when we first did this calculation, we were using sort of the standard moire Hamiltonian, and we weren't using a proper subtraction scheme. And it turns out that doesn't work. You need the moire to stabilize the lattice, and specifically through the Hartree contribution of the field valence bands. And so thanks to Jonah for pointing this out when he was visiting a while back. This was what we first found when we did Hartree-Fock at nu equals to 1 with a 6x6 unit cell without the subtraction. And you see, first of all, there are Skyrmions still. You can see these minima in the top layer charge density. The Skyrmions are still there. They're just not ordered. And it has to do with the fact that the dispersion is sort of breaks continuous rotation symmetry, so it picks out a certain direction. That direction is not commensurate with the moire. But then once we include this Hartree contribution from the valence bands, it sort of pins the Skyrmions very nicely in place, and we get this very nice lattice. Right. So here you still have Skyrmions, they're just not ordered, and that makes sense because the Skyrmions are really driven by the interactions, and the moire is sort of necessary to hold them in place. We can look at a phase diagram of this hole. You can see that for very small displacement, so this here is the strength of this background potential, but for very small UD, you can have regular hole excitations as well. But in a lot of the region, you actually have the Skyrmion vacancy as the lowest energy hole excitation, and at large UD, we get some weird symmetry breaking Skyrmion vacancy. I can talk more about that if anyone's interested. Okay, the second technical comment is that Hartree-Fock band mixing is necessary to capture this. So what do I mean? We did a numerical experiment. So we can do Hartree-Fock at nu equals to 1 minus epsilon with and without projecting to this lowest nu equals to 1 Hartree-Fock band. So we have a nu equals to 1 Hartree-Fock band basis, and we can now do Hartree-Fock at 1 minus epsilon with or without projecting to that. And this is the result. So when we project to the lowest nu equals to 1 Hartree-Fock band, we get this state, which basically is a Skyrmion lattice, and then you sort of have a little bit of missing charge in the middle, which is what you expect from a regular hole. But if we do not project to the lowest nu equals to 1 Hartree-Fock band, we get what we want. We get the Skyrmion vacancy. And that kind of makes sense because the lowest Hartree-Fock band you can think of as basically the lowest Landau level formed by a mixed Skyrmion texture, by a fixed Skyrmion texture. So if you want your whole excitation to change the Skyrmion texture, you really need to mix in these higher Hartree-Fock bands. And there's a sharp distinction between these two. If you can integrate the Skyrmion density, and they give different numbers. Also, these many body states have different rotation eigenvalues. So they're they're quite so they're different. How much time do I have?
You're out of time.
Okay, so I'll skip this last bit. But I think that these Skyrmion vacancies are probably the carriers, and they probably have interesting. It might be related to this extended quantum anomalous Hall effect, where they see this Chern 1 state across a whole range of fillings, and this current-driven thing might be related to depinning of these Skyrmion vacancies. All right, and that's my conclusions. Whoops, and let me acknowledge my student Tishuan Tan and Patrick, and some of our results, but not all, is in this preprint. Thank you.
Learn when I need to stand.
When Skyrmions were proposed for the new first one quantum Hall state, the main experimental support was from looking at the magnetization as you deviate from one, and magnetization went down very abruptly. You have an analogous effect here.
We did look for this. We did
the layer polarization. Right?
Yeah, we were looking for whether, as you dope these Skyrmion vacancies in, whether the layer polarization could change by more than would be allowed, but it doesn't. It's sort of.
What's the difference between the two problems?
The quantum Hall Skyrmions can be very big. Here, the Skyrmion vacancies are always basically on the Moiré scale. They can't be that big.
So if I remember correctly, in the experiment, the anomalous quantum Hall is seen for one polarity of the displacement field when the electrons are pushed more away from the Moiré than the other. So how to understand that? Do you understand that?
We didn't. Yeah, we didn't understand. The simplest explanation is that once it's close, then the potential and the interactions are doing opposite things. The simplest understand. Actually, we haven't done calculation for the Moiré proximate side, but the simplest picture would be that there you sort of have a single particle Chern band, and then the interaction sort of can't undo that.
Andrei.
It's Chern 0, right?
Well, the experiment also sees a Chern 1.
There's Chern -1.
Chern -1.
Proximals.
Yeah, the Ray-Achuri's experiment.
So in terms of, so let's separate the Skyrmion, the collective pulse part from the mechanism part, because I think they can be quite different, right? So I agree with the nice collective mode structure in the Skyrmion interpretation. That the Skyrmion interpretation basically just comes from the charge of the Hartree-Fock state projected to some first two layers, right? So you'd get. My point is that no matter what mechanism, whether it's anomalous Hall, which now we know it's not, or Moiré driven, you still get the same hierarchy of modes, right?
Yeah, well,
this mode changes because of some Moiré.
It has to be interaction driven.
Everything is interaction.
Yes, but like it's not a single particle Chern band. That's all I think everyone agrees on that.
There's never a single particle.
Yeah.
Chern band would be 5 for a single particle for this case. But right.
So I can't I mean, what is the difference between the possibilities that you're suggesting?
Well, for example, in this case, if I don't have the Moiré, I don't get this ground state, right? So in effect, those things would be maybe some low-lying modes, but certainly this won't be the ground state. You agreed with it, right? That you need this.
Yes, I mean, it's at the end of the day, it is like our picture is that Skyrmions are sort of interaction induced, and whether it forms a lattice or not at the Hartree-Fock or beyond the Hartree-Fock level is really hard to answer. But for the model that we have, if we don't have the Moiré, it does not form the commensurate lattice. At least.
And if you don't have the Moiré in the Coulomb, i.e. the Moiré capacitor effect, German jumping for a long time, right? They need this Moiré in the Coulomb.
In the Coulomb, yes, exactly. Just the Moiré by the tunneling is not enough. Yeah.
Okay.
I agree. Yeah.
You agree with that?
Yes. I mean that's what we found.
That's good.
Yeah. That thing.
For 2 years, this was disagreed.
Jonah.
In the picture on the left.
Yeah.
Is there any reason that this might be the parent state of the chiral superconductor? Is there any way you can?
That's what I have. That's what I'm speculating about. Is that without the moire, the Hartree always wants to form these skyrmions. So the skyrmions are really there and they're really energetically favorable. The true ground state without moire is probably liquid of these skyrmions. And if so, then that might be the parent state of the superconductor, and maybe there's something that one can do there. I don't have anything concrete to say to that at this point.
I'm technically, how did you get the collective modes? RPA?
Time-dependent Hartree Fock. So this is time-dependent variational principle in the space of Slater determinants.
All right. So no further questions. Let's thank Trithep again.
All of that.
If Jonah hadn't come, I would have probably had to choose something.
So he did like make up.
Relatively so.
Okay, so first I would like to thank the organizers for providing me this opportunity to present our recent work. So the title of this of my talk is about this orbital magnetization and susceptibility of interacting electron systems. So my name is Jian Kang from Shanghai Tech, and this talk will be basically based on those two prints. Okay. So first, I would like to say a little bit about the outline of my talk. So first, I will talk about the motivation for doing this project. Why should we care about the orbital magnetism for interacting systems? And I will talk about basically the formula, the derivation of this orbital magnetization and its susceptibility. And finally, we will. I also want to basically apply these formulas to study what is the orbital magnetism or orbital magnetization for interacting PM model. So first, usually, in classical metaphysics, when we talk about this magnetism, of course, the first thing we can think of is always this spin magnetisms, which is believed to basically have the largest contribution to magnetism. For example, if you look at the spin, you can have this ferro, you can have this spin density wave, or this antiferromagnetism, or you can have you can also have this so-called auto magnetism, which becomes a very hot topic in the past several years. Now, however, if you look at all this spin magnetism, one thing we noted that is always proportional to the electron density. So basically means that if you look at these Maria systems, and we know that this Maria systems has a very large unit cell. So basically means that the active electron, if you look at the density of these active electrons, they're very small. So basically means that spin magnetism in these materials actually is surprised by this large size of this Maria unit cells. If you look at a different contribution, which is called the magnetism, for example, if you look at the orbital magnetization, naively, just from this classical physics, we know that it can be written as this I times S, where this I is current, and this S basically is area of this electron circular motions. Now, in a typical system, this S is basically is like the size of this unit cell. So basically, it means that if you look at the orbital magnetism per unit area, again, actually this is not suffered or actually is not suppressed by this large size of the Marie cell. Now, also, I mean, all this two-dimensional in all this Marie systems, we know that it can it can spontaneously break time reversal symmetry by interactions, and also for this phase, we can have this orbital magnetizations. Now, in experiments, we know that is in principle it can be measured by discrete or this MCD. For example, if you look at this. This is like the earliest measurement of the orbital magnetization I can find for twisted materials. So it basically gives you that if you look at this measurement, I mean, it tells you that the orbital magnetization per unit cell is about like 3 or 4 μb's. Also, I mean, in this Marie cells, we know that this orbital mechanism can actually interplay with the magnetic field, and sometimes it can induce, or the magnetic field can induce some appearance of this new phases which cannot be discovered, or which cannot be found at zero field. So with all these experiments, with all these materials, we know that is very important. If you want to understand its magnetic behavior, it's very important to know or to study what is orbital magnetism for interacting systems. Now, however, if you look at the current status, actually we don't have any theory to basically to understand what is orbital magnetism for the interacting systems. So far, if you just look at the history, if you look at what we already know, most of the time, I mean, we have a full understanding of the orbital magnetism for non-interacting systems. So this theory or this formulas actually was developed mainly by 2 different groups. One is by this Professor Chen Liu, and another is Professor Vanderbilt and Resta. So about 20 years ago, I mean, they figured out what is the formula for orbital magnetization. So naively speaking, I mean, if you just imagine you have an electron wave packet, and you look at this orbital magnetization associated with the electron wave packet, it can be roughly decomposed into 2 different parts. One is so-called self-rotation part, which basically means that this electron wave packet can rotate around its center. Okay, so this is called self-rotation, and another part is called the loop circular motion. That is the center of this wave packet just doing some loop motion in the real space. So also, if you look at this or these papers, they have this formula to calculate or to obtain what is the orbital magnetization for this long-interacting systems. And all this UNK or this H is just the Bloch states and the associated the Hamiltonian for the long-interacting case. Okay, and also, I mean, which I did not. If you look at the derivations, many, I mean, they basically, the derivation actually is basically 2 different approaches. One is so-called the semi-classical equation of motion, and another one is you go to linear basis and you try to write down what is orbital magnetization. Okay. Also, I mean, also use this semi-classical equation of motion, you can obtain what is orbital magnetic susceptibility for non-interacting systems. Okay. However, if you look at all these 2 different approaches, you realize that it's very hard to generalize those 2 approaches to interacting systems. Okay. So the question is, what happened? I mean, what is the orbital magnetism for interacting systems? Now here, I just I will first, I mean, I will give you what is the result. It turns out that the formula itself actually is very similar to the long-interacting ones, with the only difference that is for the Hartree-Fock approximation, I mean, the formula is quite identical, with the only difference that is if you look at this Hamiltonian, if you look at this states, that you just replace this stuff by its Hartree-Fock counterparts. Now, naively, you think that this is not surprising. Why? Because the Hartree-Fock in principle is just really just mean field approximation. So it might be naively thinking, you might think that it's not surprising that this formula actually is identical to the long interacting one. How you do this? You actually you miss one important thing, that is during this Hartree-Fock approximation, in principle, you have this Hartree and the Fock potential, and in principle, they can depend on magnetic field. Okay, so in this sense, I mean, it's quite different from the long interacting problem, because in principle, you should include this field dependence of Hartree-Fock potential. So it turns out that it's quite surprising that the formula for M actually is still kind of like identical to the long interacting formula.
Excuse me, is En here also the Hartree-Fock energy?
Yes, everything is Hartree-Fock. Okay. So before presenting the formula, before presenting this method to derive this formula, I want to spend like several minutes just to understand, or just to give you some idea why this orbital magnetization or orbital magnetism is very hard to investigate. Okay, so first, I mean, what do we mean orbital magnetism? Okay, so how this magnetic field enters into the Hamiltonian is different from this usual Zeeman coupling between magnetic field and spins. And here, I mean, we basically do this minimal substitution. We substitute this P, this momentum operator, by P plus EA. So which basically means magnetic field enters into Hamiltonian through this gauge field. Now, in the thermodynamic limit, I mean, no matter which gauge you choose, for example, for the long gauge, you choose A, Y to be X times B. So in the thermodynamic limit, you immediately see that actually this A is actually divergent, which basically tells you that no matter how small magnetic field is, you cannot treat this A as some small quantities, which basically means you cannot do, in principle, you cannot do some naive perturbative calculations. So also you may think that, okay, we have this from classical physics, we have this R cross P for this orbital magnetization. So let's just look at what is the average, or what is the expectation value of this R cross P. It also, in the thermodynamic limit, this position operator is not well defined. Okay, so for example, if you look at matrix elements of this position operator in the basis of the Bronx states, you immediately realize that this matrix element actually diverge. Okay, and also, I mean, there are also exist some alternative approaches. For example, I mean, one thing to deal with the M in the in-line system, that is, you just add some small magnetic field to the system, and then you look at what's the change of free energy or this ground potential, and from this you can numerically extract the value of this M. However, this numerical calculation actually turns out to is very hard to do. Why? Because let's just imagine you add some magnetic field, so immediately, which basically means in the system, you have some new length scale, which is called magnetic length. And this magnetic length actually is inverse proportional to square root of B, which basically tells you that if you want to add some small magnetic field, this LB actually diverge. However, when you do numerical calculation, you need to make sure that your system size actually is much larger than LB. So basically means that for smaller magnetic field, this numerical calculation actually costs more. Okay, it's more difficult. And this is actually just for the insulating phase. For the if the system is in some metallic phase, you also need to do this calculation at a finite temperature just to avoid the possible quantum oscillation induced by this magnetic field. Now, a second way to do this is you add some, instead of doing some uniform magnetic field, you add some momentum to the magnetic field, so that the magnetic field you apply there actually is oscillating. So in this sense, you basically you introduce like pseudo momentum Q into the magnetic field. However, it turns out that this approach is nothing but just an expansion of the power expansion of Q times LB. Well, LB is basically the magnetic net. Okay. So to summarize that all these approaches are basically, they basically suffer from this divergence of this A field. However, another issue which has been rarely discussed, that is the gauge invariance of this approach, because in all these approaches you have to assume a particular choice of the gauge field A, and it's not that easy to prove that your final result actually is independent of the gauge choice. So basically, we have all these two different issues. One is a divergence of the gauge field. Another one is whether this whole approach, whether this result is gauge invariant. It turns out that those two issues are actually the same thing. They are really just two sides of of one coin, which I would discuss. Which basically I would discuss why these are the same thing. But before doing this, let me just define what is orbital magnetization in our derivation or in our theory. Basically, we define this M. We define this orbital magnetization through some thermodynamics. So, for example, basically, if you fix the chemical potential, this is just defined as partial omega. This grand potential with respect to the B field. So if T equal to 0 for 0 temperature, this omega is nothing just the H minus mu n. And also this orbital magnetic susceptibility, that's really just a similar way. It's defined as partial M over partial B at 0 field, while the mu, the chemical potential, is fixed. So now the whole question is for the system, what is omega when the magnetic field is present? Okay. So before discussing this issue, let's just say what is the Hamiltonian we have. Yeah. The starting point or the Hamiltonian is quite general. So let's just say we have some kinetic terms, kinetic Hamiltonian H0 plus some interaction. Now for this H0, this is just a simple. It's really just your substitute. So when the magnetic field is present, you just substitute this P as P plus EA. And this interaction basically is just very usual. It's just really just density interaction. We didn't see anything about the exact form of this interaction potential. And also one thing I should mention, which actually is well known, if you do some field theory, that is for this kinetic terms, we assume that this kinetic term can be expanded as a function of the momentum. And if you look at all these coefficients, they're just symmetric under the exchange of these spatial indices. Now, the reason why we say it's symmetric is just to avoid any possible ambiguity when you do this minimal substitution. Okay, so this is very general Hamiltonian. And so let me also just do some quick review to do this self-consistent Hartree fork. So we start to introduce something called the density matrix. Basically, it's defined as a psi dagger psi. Okay, and the one thing that is in principle they're at different positions. And then once you have this density matrix, you can write down what is the expectation value of the Hamiltonian, and also you introduce something called the Hartree fork potential, which can be expressed as in terms of this density matrix. So this is really common. So this is how we introduced this Hartree fork potential and how we calculate what is the total energy. So for self-consistent Hartree fork approximation, that's simple. So once you introduce this Hartree fork potential, you have this Hartree fork Hamiltonian, and from this Hartree fork Hamiltonian, if you look at the inverse of this Hamiltonian, it's just green function, and from this green function, you do contour integral, you get back this density matrix. So basically, that means it forms a loop. Okay, you start from some density matrix, you obtain this Hartree-Fock potential, and then you have this Hartree-Fock Hamiltonian, and then you do inverse, you get green function, and then you go back, you get this this density matrix. So once this loop is done, you basically have the solution for the self-consistent Hartree-Fock. However, I just want to point out several things about this Hartree-Fock Hartree-Fock approximation. One thing is in the middle of this loop, I introduced this green function, and also if you look at thing, including the Hartree-Fock potential, including this density matrix, green function, they're all written in the real space. Okay, and also in principle, this the whole thing can still be done even when the magnetic field is present. However, the only thing or the one issue is that the whole approach, this whole almost every quantities, they are not gauge independent. So they depends on your gauge choice for the A field. So as I mentioned before, I mean one thing with all this approach to study the orbital mechanism is that it's not gauge invariant, or at least it looks that everything depends on the gauge. So now the question is, can we also rewrite everything or change this loop so that we can have some gauge independent Hartree-Fock approach? Now the answer is yes, but before presenting the method, let me just introduce something called gauge invariant green function. So initially, if you look at the definition of the green function, which basically is defined as which basically is defined as this one. So in principle, you know that this green function actually depends on gauge as long as this R and R prime is different. Okay, well, because when you do gauge transformation, clearly this G changes. However, what you can do is you can basically decompose this G, this green function, the usual green function, into two different parts. One is called this phase part, and another one is called this G tilde. Well, this phase is nothing but the integral of the A field along this straight line from R to R prime. So once you do this separation, once you do this decomposition, now you do this gauge transformation, you immediately know that all the change, when you do gauge transformation, all the change actually goes to phi, and this G tilde actually becomes gauge invariant. Okay, so I should also say that this method or this trick actually is not something new. Actually, it has already been, as far as I know, it was first used by Gorkov in his paper in 1962 or 1961, and later it also has been used by many different authors, including this Patrick Lee and many other series. Okay, but I also mention several properties of this gauge invariant green function. So of course, I mean, first, I mean, if you go to thermodynamic limit, you immediately realize that only this phi, only this phase actually is divergent, where this G tilde actually still behaves very normal, behaves very well. Okay, and also if you look you look at the translation symmetry of this G tilde, you immediately realize that actually it recovers or it recovers the zero field translation symmetry. Well, you can have this formula where L basically, if you do tie binding model, L basically is the lattice constant. So this is actually different from G, where G does not have translation symmetry at the zero field, but G tilde does. Okay, so basically this is some nice thing about this gauge invariant green function. So now the issue is we want to rewrite the whole Hartree-Fock approach into some gauge invariant one. So to do this, first we noted that many different physical properties, for example, it's like this density matrix and this Hartree-Fock potential, they can always do the same decomposition, which basically means all this stuff can be basically decomposed as the phase factor, the phase term, times some gauge invariant part. Okay. And also you can rewrite, you can express this this energy or the expectation value of this Hamiltonian into some gauge invariant quantities. So now if you go over, if you go back to look at this loop, what do we have? Okay, we have this G tilde, which is gauge invariant. We do counter integral, we can get this gauge invariant density matrix. And also from this gauge invariant density matrix, you can define the gauge invariant Hartree-Fock potential. So that is just another one missing link. That is how to go from this gauge invariant Hartree-Fock potential to gauge invariant green function. Or in some sense, we need this gauge invariant Hartree-Fock Hamiltonian to finish this last link. Okay. Well, to do this, let's start from the beginning. Let's start from this definition of the original G. Okay, which this G actually depends on the gauge. Now, I mean, we rewrite everything in terms of the phase factor times this gauge invariant piece. Okay, so you can do this with this. For example, if you focus on this Hartree-Fock potential, okay, you can rewrite this Hartree-Fock potential into some gauge invariant piece times this phase factor. This G, you do the same thing. You write this phase factor times this gauge invariant green functions. Okay. Now, however, so you look at this equation, term a gauge invariant except those two phase factors. However, if you look at the product of those two phase factors, they are not gauge invariant. For example, if you look at the first one, which is the integral of the A field from R to X, and the second one is the same thing, but from X to R prime. Okay. Well, this X is just some position, and you need to do integral. So how to obtain a gauge invariant equation? That's simple. You just times the third phase factor, which is this phase factor from R prime to. So now you have three phase factors times together. Clearly, those three different phases, they form the triangle. Okay, so this is the product of those three phases is nothing but the magnetic flux through this triangle, which, as we know, is also gauge invariant because it just depends on the magnetic flux. So this is true for Hartree-Fock potential. You can also show that this is also true for kinetic terms, which I will just skip all these details. But so far, what we have is a Liu equation, which basically every term in this equation actually is gauge invariant, which basically means it depends only on B, not on A. Okay, so that's what we basically call this gauge invariant Dyson equations. But of course, I mean, we do Hartree-Fock approximations. Okay, so one thing I want to emphasize is that this equation actually, in some sense, it tells us the response of this system to the magnetic field. Okay. So now let's go back to our original goal. Our goal is to understand the mechanisms. So for example, I mean, if you look at the orbital magnetizations, which basically is defined as the minus the derivative of the grand potential with respect to the B field at zero field. So you basically rewrite everything. Okay, so it turns out that after you do some edge, it turns out that this M is nothing but this H, Hartree-Fock Hamiltonian minus mu, which is the chemical potential, times dP tilde over dB. Remember this P tilde, this is a gauge invariant density matrix. Now, also one thing I want to emphasize is that this formula is valid not just for the periodic systems. Okay, it's also valid, as you can see, it's written in the real space. So basically means that it's valid also for pretty much any systems, including the system with the open boundary conditions or periodic boundary conditions, or even with the disorders. Okay, so for any system, it can be written in this way. So now the question is how to obtain this dp tilde over db, which is nothing but the contour integral of dg tilde over db. Well, g tilde is gauge invariant green function. Now the thing is, so this one actually is simple. How to get this? We have this gauge invariant Eisen equations, which every term just depends on b. So to obtain dg tilde over db, what you can do is you just take the derivative with respect to b field on both sides. Okay, so I'll just skip all this algebra. So I will just write down what is dg tilde over db. Eventually, so as you can see that for the interaction system, if you do Hartree-Fock approximation, dg tilde over db contains two terms. The first one basically depends on the response, depends on the dependence of the Hartree-Fock potential with respect to b, and the second term that's basically just depends on the renormalized band structure or the band structure on the Hartree-Fock approximations. Well, this v is velocity operator, which is defined as the commutator between Hartree-Fock Hamiltonian at zero field with this position operators. Okay, so this is just the Hartree-Fock velocity operators. Okay, so it turns out that when you substitute this dg tilde of db into the expression of the orbital magnetization, but you immediately get the same form, which is almost identical form as the non-interacting one for orbital magnetization, with the only exception, or the only change that is your every quantity, the Hartree-Fock Hamiltonian, this energy and this block states, they should be replaced by its counterparts on the Hartree-Fock approximations. Okay. So also you can do the same thing, very similar thing to obtain what is chi. Now this chi in our calculation basically is defined as partial m over partial b. Well, this mu, this chemical potential is fixed. So now you immediately realize that this chi, this magnetic susceptibility contain two different contributions. One is called chi band. This chi band actually has the same form as the non-interacting ones. Okay, also with the only except, I express this chi band into this green functions, but all these green functions, all these inverse mass operators, they should be replaced by the Hartree-Fock counterparts. Okay. Now this one is for K band, which is just first contribution for the orbital magnetic susceptibility. Now it turns out that for susceptibility, you also has the second contribution, which is unique for interacting systems, which basically means that this term, if you look at this term, it explicitly depends on dv tilde over db, which basically is how this Hartree-Fock potential depends on the magnetic field. So this term is completely unique for interacting system. It doesn't have any counterparts for non-interacting expression. Okay. So finally, just to summarize this formula, we see that when we calculate this orbital magnetization, when we calculate this orbital susceptibilities, we introduce this so-called velocity operator or current vertex, which in our calculation, this is defined as a commutator between position operator with this Hartree-Fock Hamiltonian, which is very different from the Bell current operator. This Bell current operator, that's just depends on the kinetic term, okay, on the kinetic term with respect to the A field. So which basically means in Hartree-Fock approximation, all these velocity operators are actually strongly renormalized. And this definition, I should also emphasize that is consistent with this so-called world identity field theories. Okay. Also, you may wonder whether this so far, this is a result of Hartree-Fock approximations, whether this can be generalized to other other methods to deal with the interactions. And I should say one interesting work was done by Mengxin Ye, who will also present her result or her method when she used this Arduino word functional. Okay, so she'll give another presentation basically on Friday. So far, I mean, that's everything about the formula, the derivations. Now, of course, I mean, we always want to apply this formula to some interesting physical questions to calculate what is the orbital mechanisms. Now, so what we did, or in the second part of this talk, basically, is we want to apply this formula to the so-called the interacting BM models.
2 minutes.
Okay. Okay. I think okay. I will just quick. So basically, what we do is we look at this interacting BM models, and we look at what is the ground state at this filling equal to 3. Of course, I mean, as we all know that at this particular filling, you can get this so-called Chiral insulator, which break time reversal symmetry, and in principle, you can have this orbital mechanizations. Now, so so for zero field Hartree-Fock Hamiltonian, what we do is we do some like common things. We basically, for narrow bands, we have this Hartree-Fock Hamiltonian, but for all these remote bands, what we do is we just have this BM model Hamiltonians. Okay, which basically means that the time reversal symmetry breaking occurs only for these active bands. Okay. Okay, we know that for interacting for BM, in principle, we have infinite number of bands. So for this infinite number of bands at in the remote part, I mean, do they contribute to the orbital mechanism, or in particular, I mean, do they have any contribution to the orbital mechanization? Okay, now usually you may think that the answer is no, because for all these remote bands, they do not break time reversal symmetry. You look at its Bloch states, you look at its energy, or everything is time reversal symmetric for this remote bands. But it turns out that when you really do some numerical calculation, you immediately realize that they do have some contribution to the orbital mechanization. Now, why do they contribute to orbital mechanization even when they do not break time reversal themselves? So you start from this expression. What you can do is you can rewrite this expression. For example, you can rewrite in this way. So first you sum over all the occupied states for this UN, and then this psi is all these empty states. Now, if UN actually is in the remote bands, so how can they contribute to the orbital mechanization? That's because when this psi is at the empty state of the active bands, now you have this overlap, and in principle, this overlap actually is non-zero.
You're beginning to cut into Q&A.
What?
You're beginning to cut into questions.
Okay. Okay. So in principle, okay. So they do contribute to M, and actually you can also say if you do not include any remote bands, I mean the orbital mechanization you obtain is very small, which basically is like a 0.2, 0.3 Bohr magnetron per unit cell. But when you include all these remote bands, you have something like -3, -4 magnetrons per unit cell, which actually is comparable to what you observed in the experiments. So finally, I will just introduce my collaborators. So for the formula, for the first work, this was done with the Min-Shan Wang and Professor Oscar Waffer. And for the calculation of the orbital mechanization in twisted binary graphene, this was done with the Pinjoni, this Kun Jiang and Xiang Wang and Professor Yi Zhang. Okay. And finally, this is a conclusion part. Thank you.
Questions?
Thank you. Very nice talk, John. So imagine that you choose some algorithm to converge Hartree-Fock of your choice. Say you take an ODA. Your resulting state is not a pure Hartree-Fock or a pure Slater determinant, right? So then the question is, what should I expect from applying this formula on this resulting state to a computer?
Why is it not?
Why is ODA? Is it B
Convert
squared?
to ODA, you get slightly determined.
Yeah.
You're getting the projector out because you take B square, and then it depends on lambda, the mixing term.
As long as you can do Hartree fork, then you can apply this format.
Very nice question. Suppose that you apply what you are doing to a simplest possible case, Fermi liquid,
Mm-hmm.
and we'll try to calculate orbital susceptibility or diamagnetic susceptibility for interacting system.
Mm-hmm.
I can do this in two ways. One is basically as you think, as another one is just like calculating current correlator and taking Q square and current correlator.
Mm-hmm.
You get the same results.
I would say for non-interacting, definitely is the same.
No, for non-interacting, no question, it's the same. Yes.
For interacting system, I think it could be different because.
Can you check this? By doing, say, taking a system with, say, Hubbard interaction, doing Hartree fork, and just comparing the results.
Okay, so I did this a long time ago, and for Hartree fork, I think so we have this. So we have those two contributions. I remember if you do Hartree fork, then this term actually is 0. I mean, for Hubbard interactions. That's what I remember.
Yeah, the problem is 0 in both cases.
Then I didn't check the first.
It will be interesting to check
Yes.
what happens. And the related question is this, it's also very naive. There is a statement in the literature I grown up with that paramagnetic contributions, that spin contribution susceptibility is expressed in terms of Landau parameters, etc. It's like it's universal. And diamagnetic contribution is not, because it doesn't come from the Fermi surface.
Right.
For non-interacting fermions, the contribution comes from the Fermi surface. So the question is what happens when you add interactions, whether you can absorb all non-Fermi surface effects into Landau parameters and express diamagnetic contributions also in terms of something. I guess nobody answers this question so far.
I see. Yeah, I don't know the answer to this question.
That you have formulas, so you can do all calculations explicitly.
Yes.
Andrei.
So in the TBG, in the number,
can
you go back to the slide for the TBG, the number of bands to saturate the.
You mean this one?
Next one, I think. The next one. Yeah.
This
That
one.
So is that number of bands per valley or total? No,
It's per value per spin.
per valley per spin.
Yes.
If I just introduce the 4 remote bands, 2 up, 2 down, and then
So I
what
think
do I get if I introduce if I keep only the 4 remote?
so. If you have 4 bands, then it's pretty much here. So it's close to -3, slightly above that.
Close to the saturation.
Close.
So the contribution comes from what's the Van Hoves of the other band, or what? So if I introduce just these dotted bands, I get close to saturation, right?
Yeah, right. So basically we increase more and more bands.
And second question was, so if I have to focus on the superconductor, if I don't have the one,
That's a very good question. In principle, you cannot apply this method. You cannot, because it breaks your 1 gauge symmetry.
Sorry, Jonah. I had a question, but now I'm not sure it's the right question. So if you do Hartree fork in monolayer graphene, there's a divergence with the UV cutoff. I would assume something similar happens here in twisted bilayer graphene at high energies.
So let's say for monolayer graphene, you want to calculate. Of course, I mean you can, for example, you can do Hartree model, and you have this. You break time orbital symmetry and this. So you want to calculate the orbital magnetization, or you want to calculate the self-rotation part.
Let's say I just want to calculate M orb in a.
Then it does not diverge.
And that's this result here, which is
He's asking you something else.
Mhm.
He's asking you, there is a log renormalization of velocity in a monolayer, but this is not included in your calculation because you froze the remote bands.
Right. The remote bands are frozen.
Okay, so then you're using a not perfectly self-consistent Hartree-Fock state. Right. You're fixing the
Right. I totally agree. So this is really just the first try to look at. Of course, I mean now in the future, I mean we want to do some real self-consistent Hartree-Fock. So all this issue actually is in zero field Hartree-Fock calculation. Right. Yeah, I totally agree. Because the remote bands are frozen.
Does this only apply to density interactions, or can I have non-density interactions?
It depends on whether the interaction part is gauge invariant or not. That's a real issue. If it's, for example, I mean, density, we definitely know that it's gauge invariant. Now, if you have if you break your one gauge symmetry just in the interaction part, that you may need to have a different form for the interaction.
No further questions. I think Jian again.
All right.
What's going to be about?
Yeah, they're not. Oh, yeah.
Without the rate, yeah, right? You have P1 plus 1 minus lambda P2, right? If you urge to the right, then you will get definitely. And I believe
You want to say
tomorrow.